Then welcome everyone to the first international conference on workshop on compilers, deployment, and tooling for Edge AI, CODAI. First, I would like to introduce myself. I'm Michael Kleiber. I'm with Encharge AI, and I'm also one of the co-chairs of CODAI. The other co-chair and also general co-chair is Sebastian Vogel with NXP. So ESWeek is now almost over, and we hope every one of you has enjoyed it so far. So hopefully you have attended insightful meetings, inspirational presentations, and met really cool, interesting people, and of course enjoyed all of the amazing talks. Today it's my pleasure to present a high-class program with top contributors, both from academia and industry, for today's CODAI workshop. So the mission of CODAI is to bring the energy of the AI compiler and accelerator communities together, from academia to startups, big corporations, and open source communities. We have all of them here actually today. We have 9 great contributions for you today, among which are 2 keynotes from leaders of the AI compiler world and AI hardware world. So before diving into the first talk, we would first like to thank everybody who made it possible to have this CODAI workshop today. So first of all, I would like to thank all the speakers, all the authors of the papers who are presenting today and who contributed with the submission. I would also like to thank our team of reviewers who ensured the academic standards for this workshop. I know it's pretty tough making the deadlines for the reviews, so thank you for that. And of course, we would also like to thank the ESWeek committee, IEEE, for hosting the main conference of this workshop and their great support. Then last but not least, I would also like to thank our session chairs for today, which are Sebastian Vogel, Dennis Rieber from Bosch, and Diane Rice from University of South Florida. So thanks again, everybody I mentioned, and hopefully I haven't forgotten anybody for the great contribution. So now let's come to the first keynote, so the first talk. So it's my pleasure to introduce Kailash Gopalakrishnan. Kailash is the founder and chief product officer at Encharge AI, a startup focused around bringing transformative AI compute technologies to edge AI systems. Prior to his role, he was a fellow at IBM, where he technically led and managed large worldwide efforts on AI hardware, AI software, and AI algorithmic efforts across IBM research and various business units over the past 2 decades. His team has led cross-stack innovations in computer architecture for AI chips, low-precision arithmetics, advanced as well as AI compilers, resulting in a wide adoption of low-precision techniques across the industry spectrum. At IBM, his work enabled low-latency transactional inference for a wide spectrum of industry verticals, including finance and healthcare. Kailash received his master's degree and PhD from Stanford University in California and his bachelor's degree from the Indian Institute of Technology in Bombay. His keynote has the inspiring title, "The Past, Present, and Future of AI Compute Platforms." And with that, I would hand over to Kailash. So thank you very much for being here today.
Thanks a lot, Michael. Let me start by sharing my screen. Are you able to see the slides right now? Okay, perfect. So again, thank you again, Michael, for the generous and kind introduction. It's a great pleasure for me to be here. And I want to start by thanking the CODAI organizers for inviting me and for organizing this wonderful workshop Lots of great topics and speakers, and very excited to be here. So thank you. My hope in this keynote today is to share a very broad industry perspective on some of the key innovations in AI chips, AI systems, AI algorithms, and AI software for both deep learning training and inference that have propelled the AI industry, hardware industry over the past 5 to 10 years. We'll also share some recent advances in terms of what is the outlook for AI hardware and AI systems, both in the data center and at the edge, especially as we look ahead in the next decade. Now, I should point out that some of this work was done jointly with many of my former colleagues at IBM Research, so I would like to thank them as well for developing some of these industry-leading advances that I'll be sharing with you today. So as I'm sure you know very well, AI and deep learning in particular have had amazing success in a whole host of applications, including speech, vision, NLP, recommender systems, genomics, drug discovery. The list goes on and on and on. And it's enabling critical business automation in a whole host of industries. In some domains like computer vision or application domains, the model sizes have stayed pretty stable. But in other domains like NLP, the availability of super large data sets have enabled the creation of exceptionally large models. The picture here shows how the model sizes defined in terms of the number of parameters and model flops that measure computational cost have grown dramatically over the past 3 years. With the introduction of trillion parameter models, we see that the model sizes have grown by more than 4 orders of magnitude, while flops have increased by almost 5 orders of magnitude in just these past few years. So really super exponential growth in model capacity and flops. So this dramatic growth, of course, poses huge constraints on the kinds of hardware and system infrastructures that you need to build to support both training and deploying these models. This is, of course, especially a challenge because silicon scaling has saturated and therefore cannot, going forward, yield the density and power improvements needed to support this exponential increase that you see here. Of course, another critical business trend is the need to push AI deployment towards the edge. That's driven by latency constraints as well as privacy regulations, as I'm sure all of you know. And this has obviously driven the need to deploy these complex AI models on highly resource-constrained edge devices. Specifically, area, cost, power constraints have further expanded the need to drive these exponential improvements needed for energy efficiency. So to handle this critical challenge, teams around the world have invested in approximate computing techniques to improve the energy efficiency and throughput of AI chips and systems. The basic philosophy here is that AI broadly, and of course deep learning in particular, is conceptually similar to how the brain processes information. And since the brain does not do exact computations, we could leverage inexactness in algorithms and hardware substrates to get higher computational efficiencies. And if you look at this chart, you see that there are a whole host of approximation techniques that could be applied to AI applications. So at the top of this chart, you see pure algorithmic and software techniques. For example, approximations in input sampling, relaxed synchronization techniques, and so on and so forth. And many of these techniques have been studied in depth and also been adopted widely in AI training systems today. In the middle of this chart, you see the focus on approximate architectures. So one really exciting way to enable that is via low precision arithmetic. But one could even delve down deeper and implement approximate circuits and even build approximate devices and silicon that essentially enables native hardware support for approximate computing. The key point here is that these gains become dramatically higher as we exploit these techniques in hardware. And the rough rule of thumb is, for example, is you get a quadratic gain in throughput and energy efficiency with precision reduction, and it applies to both training and inference systems, as you'll see in the next few charts. For example, a 4-bit system can be up to 16 times more efficient than a 16-bit system and 64 times more efficient than a 32-bit system. So the obtainable gains are very, very significant. However, the key challenge is that it's very critical to preserve AI model accuracy while reducing the precision of the arithmetic. A lot of the work done around the world focuses exactly on this topic. And as you will see through a combination of algorithmic techniques, careful design of integer and floating point formats, And through hardware-software co-design, the industry has made lots of progress over the past decade towards enabling these higher and higher efficiency systems. From a future-looking perspective, my view is that the gains in low-precision arithmetic have mostly saturated and are expected to saturate over the next few years. And the next big leap towards these higher efficiency systems is to leverage the use of approximate analog computing techniques in deep learning systems. So I talked about precision scaling being a critical knob in AI system performance. And indeed, the AI hardware industry has moved aggressively towards exploiting these techniques. So if you look at prior to 2015, all of the AI computations, whether it's for training or for inference, were essentially done in FP32 arithmetic. However, the industry has since then moved aggressively towards reducing the precision of training systems, which
Kailash, your audio is somehow gone.
And so I have actually and also the recording because we often have.
Do you hear us?
Yeah, I can't hear him also.
He seems to hear us. I think he reacted.
that's it. Can you hear me now?
Yes.
Oh, sorry about that. My wife, I think, turned on her AirPods and it took away my speech from here. So, okay. Where did you lose me? Just so I can restart there.
30 seconds ago.
30 seconds ago. Okay. So let me start again on this chart. So I talked about precision being a critical knob in AI system performance, and indeed the entire hardware industry has moved aggressively towards exploiting these techniques. So prior to 2015, all of the AI computations for both training and inference were essentially done in FP32 arithmetic. However, the industry has since then moved aggressively towards reducing the precision of these training systems, which are largely data center-based chips and systems, into FP16 arithmetic, and the precision of inference systems, which are both data center as well as edge-based, into int8 arithmetic. Now, focusing on training systems, much of the training in the world today is actually enabled using FP16-based AI hardware, which has now been shown to be roughly 4 to 8x more efficient than FP32. Various FP16 design formats have been proposed and are used widely in various AI training systems, including in GPUs and TPUs and IPUs and so on and so forth. And if you look at all of the different work out there in the industry, you see that the industry has explored 3 different floating point formats. I'll talk about them in some detail in the future, but certainly the critical trade-off between these different floating point formats for AI is all about trading off dynamic range for precision, so exponent versus mantissa bits for floating point support. From an inference perspective, most inference chips today support floating point 16 as well as the standard int8 format. And the reason for that is the int8 format is 16 times roughly more efficient than floating point 32. However, the reason FP16 is still being considered for inference is because, of course, if you train a model in floating point arithmetic, you can directly use the model towards deployment without the need for any additional quantization. Now, if you talk about int8 quantization, the quantization of an AI model to an 8-bit arithmetic, there are 2 different techniques that can be employed. One technique, of course, uses the trained model and applies quantization on that model, considering, for example, the minimum and maximum ranges of the tensors. This is referred to typically as post-training quantization, or PTQ. And of course, sometimes PTQ does result in an accuracy loss for AI. So as a result, in the industry, there's been a lot of work to look at training the entire model again while implementing quantization. And this is typically what is referred to as quantization-aware training. So quantization-aware training, of course, results in excellent model fidelity and is indeed now the de facto technique for low precision quantization, especially as you reduce the precision below 8 bits. So the success of the introduction of 16-bit formats for training and 8-bit formats for inference led us a few years ago to the inevitable question, is there more? And specifically, can we scale the arithmetic precision even further in order to improve the performance and the energy efficiency of AI systems, while all along fully preserving model fidelity? This is a research that was done in various institutions over the past 5 years, including in my former institution, IBM Research, where basically, and various universities as well as industry partners. So the way to think about the scaling of precision further is similar to how technology scaling has improved performance exponentially. The precision scaling roadmap was proposed back in 2016, where the goal was to figure out essentially innovative algorithmic techniques through true hardware-software co-design, through introduction of novel integer and floating point formats, and many such related techniques to scale the precision by roughly 2x every 3 years, all along while fully preserving model fidelity and accuracy. So this is what you see on this chart. This is what we refer to as a precision scaling roadmap, where we plot precision required versus years, and where the green curve represents essentially the bit precision needed for training, while the blue curve represents the bit precision needed for inference. So to showcase a couple of critical advances through both fundamental as well as empirical techniques, teams around the world successfully introduced techniques in 2018 and 2019 to do 8-bit training for the very first time. And I'll share some advances on that as well in the next few charts. And simultaneously on the inference side, introduced new ideas to scale the precision down to 4 bits from 8 bits. Similarly, in 2020 and 2021, there were a ton of new ideas that enabled the training precision to be further scaled down to 4 bits, while making even new strides towards lowering inference precision down to 2 bits. What I hope to do in the next 30 minutes or so is to walk you through some of these key innovations that the research community has driven that have enabled these transformative advances, starting with training systems first, followed by inference systems. Now, I also strongly believe that over the next few years, we will reach the end of this precision scaling roadmap. And as a result, we are seeing a move in the industry towards analog computing techniques. The key insight here, of course, is that if the application can leverage it, analog computing can provide a further 20 to 40x enhancement in performance and energy efficiency. So of course, here at Encharge AI, we are truly excited about the potential for precise analog computing and the AI applications and ecosystems it can truly enable. So as I mentioned before, FP16 formats have now become standard in the industry since their introduction in 2017 for both training and inference. So around that time, the worldwide research community started looking into techniques that would enable scaling the training precision down to 8 bits. 2018 marked the first research advances in this direction, and there were 2 critical publications that were released then that highlighted these advances. One of these papers was from Intel Labs, and in this work, they showed that 8-bit integer quantization techniques were used to quantize weights, activations, and gradients seen in deep learning training. There was a first demonstration of 8-bit integer quantization for training, and it introduced a number of new ideas to enable that 8-bit training, for example, by changing the way you do normalization in deep learning models and so on and so forth. However, the critical problem was that out of the 3 computations that you have in any deep learning training model, the forward, the backward, and the update, only 2 of them could be done in low precision arithmetic. Therefore, the overall advantage gains were lesser than expected. From a results perspective, the Intel team showed a lot of different kinds of networks, but the data sets were much smaller and limited. And therefore, the understanding ended up being that this technique, while applicable, is not scalable across a wide spectrum of models. The other interesting paper that was also introduced in 2018 came from my former team at IBM, where we introduced the use of these floating point 8 formats, FP8 formats, for training deep learning models. This is the format that's shown on the right here, where we essentially show that all of the computations that you need to do for deep learning training and all of the tensors that you need to represent, weights, activations, and gradients, everything could be computed using FP8. And to enable this innovation, we introduced a number of novel ideas in addition to the number representation format, including the idea of doing chunk-based accumulations, or what we refer to now as hierarchical accumulations, the use of stochastic rounding techniques for weight accumulation, and so on and so forth. So using these techniques, the IBM team was able to show excellent accuracy with floating point 8 in a wide spectrum of computer vision models, including ResNet 15, ResNet 18, ResNet 50, and so on and so forth, with no loss in accuracy. So these advances in 2018 lent credence to the belief that you could in fact do precision scaling even for training, and that 8-bit training was a real possibility in the future. So while the previous work on FP8 seemed to show excellent promise for most models like ResNet 50 and CNNs, teams around the world noted quite soon that the FP8 had significant challenges, especially when working for either constrained models like mobile nets or newer models like transformers. The key issue here lied in the challenge that a single floating point 8 format, number representation format, was not suitable to represent both weights, activations, and gradients during deep learning training, given how disparate these different tensors were in terms of range and representation needs. So to get around this problem, our team in 2019 proposed the use of what has now become an industry standard called hybrid FP8, where two different FP8 formats are used during training. And these are the formats that are shown on the right side of the screen here. Specifically, weights and activations need higher fidelity, but less of a dynamic range, and therefore can be represented by this 143 floating point 8 format, while the gradients need higher dynamic range, but lesser fidelity, and therefore are represented with the original FP8 152 format. The team also proposed novel round-off residual schemes that allowed for low precision gradient accumulation, and also backed that with solid theoretical analysis to show that this theoretical convergence is guaranteed for AI models using FP8. So overall, the work showed that the hybrid FP8 works exceptionally well across a wide spectrum of models, including mobile nets, transformers, efficient nets, speech, object detection, all while fully preserving accuracy. A critical advantage of FP8 that was shown at that time as well was the concept of what we refer to as trans-precision inference, where we could train the model in FP8 and that could be directly deployed for inference without the need for additional quantization of our training, which is a distinct advantage of this format for inference over the int8 format. And of course, all of this was initially shown from an algorithmic perspective, but over the past couple of years, as I'll show you in the next couple of charts, a lot of these has been deployed in hardware, demonstrated in hardware, deployed in hardware, and quite recently also adopted by various industry titans, including NVIDIA and Intel. So as mentioned in the previous chart, a lot of these FP8 concepts were demonstrated in multiple products and presented at various forums over the past 5 years. So recently there has been a move by various industry leaders to standardize these FP8 formats to make sure that the data types can be easily ported from between platforms, for example, between a CPU platform and a GPU platform and between different CPU platforms. So of course, when you think about the hardware implications of these FP8 formats and what we refer to as hybrid FP8, there's of course a lot of complexity associated with two different formats, right? We have to support two different mantisas and two different exponents. And so a lot of the innovations in the hardware space over the past 5 years have been focused on how do you merge all of these different formats into a floating point unit that's very compact and efficient. And one key innovation from a hardware perspective was the combination of these two formats, along with a floating point 16, all designed and implemented on the same engine, which was built in various chips. And one example of a chip is shown on the right side of this slide here. So to give you a sense of the improvements and the efficiency that you gain from FP8, typically, if you compare FP8 to FP16, an FP16 engine gives you about 2 TOPS per watt in terms of efficiency, while a hybrid FP8 engine can give you a good range somewhere between 4 to 10 TOPS per watt in scale technology nodes. It's a good factor of 2 to 4x, maybe even higher energy efficiency using these FP8 formats versus the traditional floating point 16 formats. Furthermore, as mentioned before, FP8 can be very aggressively applied towards both inference and training systems. So there's a lot of cross-platform compatibility that can be leveraged using FP8. So I wanted to take one step beyond the FP8 because FP8 has now become an industry standard. It's in the process of becoming an industry standard. A lot of chips out there today support FP8. So what's the next step for training? And if you look at what the next step for training is, certainly with FP8 becoming largely a solved problem, the research community has now moved to innovations that can enable reducing the training precision below 8 bits. In other words, how do you do 6-bit training, 4-bit training, so on and so forth? And of course, the goal is to improve the throughput and performance of training systems. So in the last couple of years, there were a number of novel ideas that have been proposed on this front. I must emphasize that these are very, very new ideas. So obviously a lot of work remains to get to a point where these ideas are ready for commercialization, but it's very, very promising. So one of the recent exciting pieces of work focuses around 4-bit training, where a number of new innovations focused around 4-bit floating point representations, different radices for floating point formats, adaptive gradient scaling techniques, two-phase rounding schemes, a whole bunch of new ideas have come together to enable these kinds of training systems with minimum quantization errors. Of course, these techniques, when you combine them essentially for deep learning model training, you can see that for the very first time, demonstrations have been made that where you can convert
Kailash, unfortunately, your audio is gone again.
Are you able to hear me now?
Yes.
We hear you again. Thank you. This time it was just 5 seconds.
Okay, thank you. Sounds good. Thank you. So there's a lot of exciting work here in terms of the formats for 4-bit training and the advances that have been made in just the last couple of years. And obviously from a hardware perspective, from a software perspective, the real advancement here is that 4-bit training, when it's ready, can enable up to a 7x improvement in area and power efficiency over 16-bit trainings. There were lots of work published in various conferences over the past few years. I just want to highlight that there's a lot of work happening across industry and academia that is really pushing towards further reducing the training precision below 8 bits. And I strongly believe that will happen over the next few years. While that's so, all of these results are very significant, but I should point out again that these are initial advances on the precision scaling roadmap below 8 bits for training. And certainly, I think there is some amount of work that needs to come together to enable true 4-bit training with minimal to no loss in accuracy across various data modalities. That's part of future work. So I want to talk about, I talked about training for the past few charts. I wanted to pivot a little bit and talk a little bit about inference, because a lot of the interest in edge AI systems is really all about inference. Of course, you could use floating point 4 and floating point 8 formats to do edge training as well. But certainly inference is the more widely dominates the compute requirements at the edge today. From that perspective, essentially, we talked about the use of floating point 16 and int 8 formats for inference that have been used for the past 5 to 6 years. And of course, one important thing to note here is certainly that the most common thing that is used in the data center today is FP16 inference, and that is typically because it's convenient because the model was trained in FP16, and sometimes simply because it's not always possible to have access to the data set, so you don't have the ability to retrain the model to deploy it in lower precision arithmetic like int 8. Int 8, on the other hand, is much more energy efficient, typically about a factor of 4. But we need to figure out ways by which the floating point trained static weights can now be converted to integer formats. So as discussed before, this is done either using one of two techniques. One technique, of course, is post-training quantization, referred to as PTQ, and of course, quantization of that training, referred to as QAT. PTQ is relatively straightforward and typically uses simple min-max quantizers, sometimes more sophisticated quantizers for weight conversions from the floating point domain to the integer domain. And certainly there have been a number of techniques proposed to do integer quantization of activations. QAT, on the other hand, involves either a full or a partial retraining of the already trained model and results in a much more accurate model. So this incorporates the loss from quantization in the forward phase of training. So as you can see from the table here published by the Google TensorFlow team, QAT typically results in higher accuracy loss, especially for constrained models like mobile nets. I should also mention that if you look at PTQ and QAT, that quantization of our training techniques, QAT techniques, are now the de facto standard when we need to use even lower precision inference, for example, using int4 or int2 quantizations. So I wanted to spend a little bit of time talking about some of the dramatic advances that have been made in these quantization-aware training techniques, there have been lots of innovations across the industry and academia over the past few years. And these techniques have dramatically improved accuracies for integer quantized systems, especially as the weight and activation precisions has been scaled below 8 bits. So the basic idea in these QAT systems, or QAT frameworks, is that the quantization error in these systems due to the weight and activation quantization is incorporated as part of the training loop. And essentially what this means is that the loss function has an added component that comes from the quantization-induced errors. And then using backpropagation, we simply update these weights. In other words, the network parameters get adjusted so that you can compensate for the effect of extreme bit quantization. And there have been many, many techniques proposed over the past 5 to 6 years, and essentially new and improved ones are being proposed every single day. I just want to highlight a few of them that have basically been deployed in production for the past few years. So one of them, of course, is what is called SAWB, stands for Statistics-Aware Weight Binning. It's primarily a technique that is used for weight quantization. And what it does essentially is it exploits the first and second moments of the weight distribution to calculate the scale factors and clip levels for integer quantization of weights. We have another technique that was proposed by Qualcomm called LSQ, which stands for Learned Step Quantization. And basically, it's an asymmetric quantization scheme that allows you to train a scale factor and offset for quantization. Again, it's part of the quantization of our training frameworks. And finally, the technique that is quite widely used in the industry is referred to as PACT, which stands for Parameterized Activation, and it has a whole bunch of successor techniques. And it's basically a mechanism by which you can train a clipping factor for activations, again, directly as part of the training loop. So using all of these techniques, a lot of companies and academia have successfully and aggressively scaled activation and weight quantization down to 4 bits. I should point out that in these various family of schemes, there are many different derivatives, but the most common ones that we see out there today are the ones that use SAWB for weights and either PACT or LSQ for activations. And what I'll do over the next couple of charts is to show you some of the key results that have come up based on using some of these techniques for aggressive integer quantization of the hardware. So on this chart, essentially what we do is we summarize the results when these 4-bit quantization techniques are applied to state-of-the-art AI models across various application domains. So if you look at this chart, you see many, many AI models. On the top left is object detection models. The bottom left are these transformer models. On the top right, you have traditional computer vision models. And on the bottom right are the speech, LSTM-based speech models. For all of these models, of course, the statistics-aware weight binning techniques were used for weight quantization, and the PACT techniques were used for activation quantization. And there is still a lot of black magic in quantization, so you have to do a lot of careful initialization, hyperparameter tuning. All of these are fundamental needs. But what you can see on this chart is for each of these models, and what you're doing is you're comparing the accuracy of these models for 4-bit quantization versus FP32 quantization. And in virtually all of these models, the accuracy of these models is within 0.5% of the FP32 accuracy, which is, of course, reasonable enough for deployment in the vast majority of cases. What I want to highlight, though, is that these results demonstrate that 4-bit models can show excellent accuracy, and in my view, represent the next frontier of performance and energy efficiency for inference of these large AI models. But if you look beyond integer 4 arithmetic, there is broad consensus in the industry that it is very, very challenging to reduce the precision of the weights and activations below 4 bits. Especially as we go to more aggressive quantization, the accuracy loss grows significantly. So in our perspective, quantizing below 4-bit arithmetic is very, very challenging. I wanted to take a step back from quantization and arithmetic and look, what are the other knobs we have to look beyond quantized arithmetic that might improve the performance and the efficiency of these AI systems? So there are many, many complementary innovations needed in addition to the compute efficiency gains that come from quantization to improve system performance. One exciting technique, of course, is to leverage the use of 3D chip stacking techniques to alleviate system bandwidth issues. So as we scan the full spectrum of AI applications, both for training and for inference, we see multiple opportunities for system performance improvements. For example, inference applications, especially with small batch sizes and frequent context switching, can often be bandwidth limited, especially if the data is stored in an off-chip memory. Similarly, on the training side, with very large batch sizes, applications are unable to fit their entire tensors on chip, and therefore the system becomes again bandwidth limited. Beyond some of these important small batch size applications, if you look at recommender systems, you have hundreds of gigabytes to multi-terabytes of embedding tables. And if you look at networks like GNNs, graph neural networks, you have lots of random sparse accesses. These kinds of applications can benefit dramatically from higher bandwidth 3D systems. So to enable these efficient AI solutions, the industry is moving aggressively towards 3D stacked system on chips. However, one solution fitting all applications may not happen. And the reason for that is, for example, computer vision applications will typically have the need for smaller AI models, but much higher bandwidth. So that could be accomplished using essentially stacking an SRAM chip directly on top of an AI compute chip. However, recommender systems and GNNs might benefit from much higher capacity, and they are okay with the slightly lower bandwidth. So as such, I think there are different solutions needed for different verticals. And as such, the industry is looking to leverage these heterogeneous integration techniques to provide targeted solutions for specific AI verticals. It's a very, very exciting trend happening in the industry right now. On the compute side of the equation, there are three dominant approaches being considered in the industry. The low precision approach that we have described earlier has been the predominant approach so far. But as I mentioned before, it may run out of steam over the next few years. One approach, of course, is to build on top of the quantization approaches by adding sparsity to the quantization techniques. But there are many key questions that need to be answered, including whether the sparsity can be combined with extreme quantization and whether accuracy of these AI models can be preserved. So those are all open questions that the industry is pursuing as we speak. On the architecture side, low precision techniques also open up new opportunities. And this is because low precision architectures have very low utilization typically. In other words, a sustained performance does not scale quadratically, even though your peak performance grows dramatically as you scale precision. And this drives the need for new techniques in hardware and software to enable various opportunities like pipeline parallelism, model parallelism, and of course, for significantly improved network on chip on the hardware side to basically connect these different AI cores and these different AI chips together to enable higher and higher sustained performance. Looking beyond these techniques that are already being pursued by the industry, I believe that analog computing approaches will become increasingly prevalent for AI compute. And these techniques, which I'll share in the next couple of charts, can bring forward more than an order of magnitude in energy efficiency and performance. What I'll do next is to share some of the key trends in the industry on analog computing, as well as some of my perspective on some of the key challenges to moving forward using these techniques. Now, the key reason to leverage analog computing approaches is because matrix and tensor computations, which form the backbone of deep learning and AI, can be natively mapped to physical analog silicon substrates. So specifically leveraging 2D memory arrays, one can use these analog techniques to build computational platforms that are 10 to 40x more efficient than the most efficient systems that you have today. A key advantage of this form of analog computing, which we refer to as in-memory analog computing, is that it also eliminates the data movement problem, which can dominate the energy cost for AI compute systems. And today, for example, if you look at the data movement problem, you have to take the weights sitting in memory, move them to the accelerator. And of course, that essentially that read and write of the memory technology essentially limits how efficient you can build your AI systems. So by leveraging analog computing directly inside memory arrays, we can harness the efficiency gains of analog circuits and analog compute while fully eliminating data movement costs. Of course, the key challenge in leveraging this special form of analog compute is to make sure that it's reliable, repeatable, and accurate enough for a wide spectrum of AI applications. And that is a key work that's happening everywhere. And so I should point out from an analog computing perspective, there are many, many unique technologies that can enable in-memory analog computing. And there's been certainly a huge body of work, especially from academia over the past 5 years, looking at various technologies, including SRAM-based, PCM-based, RAM-based, so on and so forth. And this chart here compares the throughput on the left and the memory size on the right as a function of various technologies, which are widely differing TOPS per watt. From the left chart, you can see that we can obtain very, very high efficiency and throughput, especially when you compare it to digital accelerators. And you can also see that the blue points on this graph typically show you that the SRAM-based versions tend to outperform the non-volatile PCM or RAM-based versions currently being pursued. Now, one key challenge in these kinds of analog computer architecture chips is to define the architecture cleanly. Because a key challenge in this architecture is to be able to integrate multiple of these analog computing memory arrays and demonstrate end-to-end neural networks. This is a key challenge that the industry is working on. And I believe this is fundamental towards enabling a future where we have analog compute forming the backbone of AI deployment. Accuracy is also a critical challenge and depends on the nature of the noise introduced by the specific form of the analog computing substrate. So that's a very active area of work as well. From our perspective at Encharge AI, we are very excited about in-memory analog computing, and we believe that analog will drive the need for high signal-to-noise ratio solutions that can be area and power efficient, and at the same time can be easily integrated into full chip architectures that can be scaled and deployed in aggressive technology nodes. Analog computing also opens up the opportunity to have lots of optimizations at the compiler level. For example, when you have 10 to 40x higher efficiencies, the questions remain in terms of how do you map an application across a wide spectrum of analog cores, and what is the most efficient way of getting performance from these systems. So I wanted to bring it all together and conclude by mentioning that AI systems is, as you've seen here, is a very dynamic space. There are lots of innovations happening across the stack in algorithms, in the compiler stack, in hardware, and lots of innovations have already come together in the past few years. And there's plenty of room to improve system-wide performance by another 1 to 2 orders of magnitude over the next decade. Leveraging low precision architectures and heterogeneous integration, including 3D stacking, and of course, leveraging analog computing approaches, in my view, the future looks incredibly bright. But in parallel to defining all these base technologies, we expect AI to evolve as well. Today, AI is all about mostly simple perception systems, and we expect that movement from simple perception to more complex reasoning systems, essentially giving the idea of AI having the notion of a common sense and helping add features like explainability to AI. This is a very rapidly evolving space where numerous techniques are being considered, including graph neural networks, coupling neurosymbolic approaches with traditional deep learning models, and so on and so forth. But one really good thing from the industry perspective is that these reasoning approaches will drive the need for a further growth in AI compute beyond what deep learning is already driving today. Finally, a key area I personally find very exciting and interesting is the confluence of AI and security. This is not just about applying AI for security. In other words, security is not just a vertical for AI, but it's really also about enabling AI chips to have end-to-end security, for example, through encryption on the links, understanding and eliminating side channel attacks on AI systems, even enabling true encrypted systems through homomorphic encryption for future AI systems. So lots of exciting work that's happening here at the confluence of how do you build these AI models that are secure, and how do you build AI chips that are secure, how do you use AI for security, and how do you mix AI and homomorphic encryption, for example. So lots of exciting work, and it'll drive a lot of work both on the hardware side and on the software side for AI. With that, I'll conclude my talk. I thank you all again for your time, and I'm very happy to take any questions.
Yeah, thanks a lot for the great presentations. So let's give a big backhands, virtual backhands for Kailash. And let's open the session for questions.
Hi, Kailash. Dennis here. You talked a little bit about the advantage of SRAM-based versus of flash or memristor-based compute units. So, but what about systems that are dormant a lot of the time and need to basically to start up, do some kind of inference, and then return into a sleep mode? Is there already some research there? How there these differences play out?
That's a great question. I think for those kinds of systems, there is a lot of value in having non-volatile memory technologies, right? I think the question though might be one of how do you so you have two options there, right? One option, of course, is to build an AI platform using NVM technologies, right? Native NVM technologies. That works, but the challenge there, of course, is the accuracies that you get from these technologies, the PCMs and the resistive RAMs, are significantly lower than what you would get from traditional digital accelerators or the other forms of analog compute. So that's a challenge. So one way, the other approach that you could apply there, in my view, is to simply integrate in a package flash memory and some of these approaches. So you don't have to keep the chip active all the time, but you can essentially transfer the weights from the flash, maybe through a 3D stack technique, directly to AI chips. There's a lot of work happening in the industry for those kinds of things. But broadly you're correct. You might find different applications and different use cases driving the need for different forms of computational substrates. Did that answer your question, Dennis?
Yeah, perfect. Thanks. Very insightful.
So further questions. We have some time for questions. We are actually ahead of time.
Yeah, I have another question regarding quantization. I find it interesting what you described in terms of int4, FP8 as these new trends. Let's say int4 is not really that new. At least I've seen it several times, mainly in the academia. But my question is more into, what is your expectation? When can we see this more into the industry, right? Because so far, well, has been mainly int8 dominated, and we are also on our side, we have seen FP16, which also is in line with what you describe.
Right.
But I'm curious about, the reality of int4 and also FP8.
So
It's
that's
a
a great
widespread
question.
solution.
So as you know, FP8 is now part of multiple AI products, right? You see in the industry today, the NVIDIA GPUs have FP8 support. Lots of other AI chips also have FP8 support. So FP8 has become, it was introduced in production maybe in the last year. So I expect it to be quite widely used in the next few years, because now people have access to it, developers have access to it, AI data scientists have access to it. They're all going to try various things, and we'll know exactly where things work and where they don't. But it looking very promising. Int4 is an interesting story because the way to think about Int4 is if you can do quantization of that training, then you have clearly a good path towards using Int4, right? But the challenge, of course, is if you look at the AI lifecycle in most verticals, some AI life cycles require deploying a new model every day or every week. When you have that kind of an AI life cycle, it becomes hard to do quantization aware training. But if you have an AI life cycle that is in the range of months, then it is much easier to insert quantization aware training directly into that workflow. So that's one answer, right? So in my view, Int4 advances have really happened to this level of accuracy, this finesse in accuracy just in the last year and a half. Prior to that, you had 2%, 3% accuracy loss. So now that you can get it to within 0.5%, the question is which verticals and what essentially can allow for quantization of our training and which ones cannot, and the ones that can will be the ones that embrace Int4. Now, a second part of it is a lot of work happening both in industry and academia on post-training quantization for Int4. So figuring out new ideas, right, by which you can directly quantize these weights without having to retrain the model. If those advances come in, then of course, Int4 becomes a much sooner reality. So the short answer is I don't know the answer, but it's certainly, in my experience, I've seen Int4 being deployed whenever the AI workflow lifecycle is long. When the AI lifecycle is short, we need a few more advances on the post-training quantization side to enable that integration. Did that answer your question?
Yes, thank you.
Sure.
Kailash, Sebastian here. I would have a follow-up question on the previous one, because I do think, as you, with this great talk, walked us through all the quantization aspects, and especially the few-bit quantization aspects below integer 8. Following upon the question that was just raised, one thing in my perception that is one of the biggest struggles within below integer 8 quantization is how to represent these networks and how to compile those networks, and making this into a more standard than the data types that we typically have, right? We do have integer 8, we do have int A16 and FP16 data types, but there is no integer 4 data type standard. And I'm wondering what your view is on the future of compilers and deployment tool chains to introduce something weird while still having the acceptance in the industry. So I'm a little bit wondering what your view is on the future here.
Yeah, I think you raised a very important point, Sebastian, which is really the chicken and egg problem, right? How do you support? I mean, even if you have hardware that does all of this well, how do you support this in a systematic way across the software stack is an important challenge, right? I think things are changing. I mean, even if I look at where things were 4 years ago when we started a lot of this effort versus where they are today, now FP8 and training has been enabled on GPUs, right? And Int4 is supported on GPUs. So I expect that essentially the ecosystems will evolve or will need to evolve to support these data types. I do agree that one of the biggest challenges in virtually any compiler ecosystem we have is essentially to support these different data formats. There is very little standardization happening in the industry right now. Thankfully, just in the last few months, the FP8 standardization has moved forward. So that's a great sign, right? I think the right step after that in the next year or so, in my view, would be to standardize Int4 formats on the one hand, and also standardize the support for these formats within various compiler stacks, including TVM and things like that. So very, very intrigued by that. Now, of course, in the interim, right, while the support for these data types doesn't exist, there are lots of techniques individual companies and verticals are employing to support under the hood Int4 support, right? I mean, you don't need technical. You ideally want to have native support for your format, but it's in some sense, if it's not exist, you have to play around with the compiler stack in the graph to make sure that you can do all of that under the covers versus being explicitly explored. So those are all interesting questions. I really personally think that, quite frankly, if from a precision perspective, I think Int4 support needs to be there in most of the compiler stacks. I think it's time, because we have finally reached a point where the accuracy levels are really, really good, which was a key challenge for many, many years. Now that those are good, not just on simple models, but on really complex models, I think at the time is right to standardize some of those within frameworks and compilers to make sure that the deployment can be done seamlessly without having to worry about some of these different things.
Thank you very much.
Thanks, Sebastian.
May I ask a question?
Sure.
Certainly, yes.
Yes. Yeah, thank you for the nice talk. I'd like to ask you your perspective on sparsification. So you have now shown whatever the quantization approach, and of course there's a parallel branch of whatever trying to make models sparse, training them sparse from the beginning. Right. And can this be combined? That's a question. And also, if you talk about at the end about analog computing, whatever the backbone are just crossbar arrays somehow. Right. Yeah? Does it make sense even to look for a sparse sparse layers when targeting these analog computing architectures?
Yeah, that's a great question. A couple of good questions there. So let me answer both of them. The first one is with regards to the role of sparsity together with quantization and where things are, right? I think the challenge is that if you consider the fact today that you can produce Int4 models with probably under 0.5% loss in accuracy, and you can produce sparse models with less than 0.5% loss in accuracy. When you combine them, you typically have 1% loss in accuracy. That's kind of the where we are today. Maybe it's more, sometimes in some cases 1.5%, 2% loss in accuracy. So that's a challenge. So I think we have to continue pushing that on the sparse techniques to be able to do that. Of course, the question also is which sparse technique. You can have, completely random sparsity, or you could have fully structured sparsity, or you could have somewhere in the middle. That's what NVIDIA does in terms of fine-grained structured sparsity. My personal view is that the fine-grained structured sparsity is the right thing to combine with quantization, because then you can leverage regularity in the compute infrastructures to combine quantization and sparsity, because it's in some sense they are both can be handled very efficiently in hardware. But there is some research that needs to be done to study the limits of combining 4-bit integer quantized numbers with sparse representations. There are some very nice papers on this very topic being published this year at NeurIPS. So certainly those of you who are interested, you should look at that. I think one from my former group at IBM and many others as well. So certainly lots of advances there. On the analog side, great question. So the question you ask is, how do you combine sparsity with regular 2D arrays, right? And that's a very good question. And it's a very interesting question, because in my head, because you get the 10-20x advantage natively with analog compute, the motivation to also push sparsity is low in my head, at least. But certainly, I think from one perspective to look at it would be that perhaps the role for sparsity there is not in essentially compute, but it's in lowering the memory bandwidth. So if you are essentially have a system where you're doing analog compute, but the weights are not all sitting on the chip, but they're coming from off chip, you could certainly leverage sparsity to reduce the memory bandwidth as opposed to the compute efficiency. So, but broadly speaking, I view sparsity as less important for analog compute. But time will tell whether that's the right answer, or if there's a different way of sparsity, especially on the weight side, that can be combined with analog compute.
Okay, thank you very much.
Sure.
Hi, Dennis here again. I actually have another question that is maybe a bit more big picture, but I think it fits quite nice with your talk. So you talked a lot about also in your previous answers about how the adoption of Int4 and FP8 in GPUs was crucial, so that it's finally also adopted into the frameworks, so people can start using it and so on. So
right.
There's a bit of this chicken and egg thing, that basically we develop architectures that work well on the GPUs that we have, because the GPUs are the best thing available right now to
right.
work on. So what do you think analog computing has to bring to the table to break this kind of cyclic dependence between architectures and hardware?
Yeah, great question. My view is that analog computing should be able to natively deploy Int8 or Int4. And if you start to go, if your analog compute drives the need for custom precision, or has lots of noise that basically prevents you from leveraging an almost integer like arithmetic computation, then it's going to be very, very difficult for adoption. So in my view, the success path for analog compute architectures is I make the analog compute we know is noisy, but the noise levels can be reduced significantly to the point where 8-bit compute becomes almost noiseless. That would be one way of directly leveraging existing Int8 infrastructures or Int4 infrastructures directly for AI deployment on analog devices. That is, in my view, very crucial, because if you have a system where the noise is so high, there is really no level of abstraction that you can build that allows you to connect it back to frameworks and compilers. You really have to have the noise level. And that's one of the reasons at Encharge AI we are excited about some of the technologies that we're working on, because it's really all about figuring out an accurate form of analog compute that preserves the existing Int8 and Int4 infrastructures as much as possible. Does that make sense, Dennis?
Yeah, it makes sense. So maybe then to follow up a bit. So when you have this architecture and you get adoption even into a framework that uses your hardware as a backend, I mean,
right.
There have been very efficient hardware accelerators before, specifically for deep learning. So like
right.
Iris, for example, they always prove to be very energy efficient. So but they never really, there was never really a big breakthrough over GPUs still in a lot of cases. So what makes analog different there?
I think that's a great question, because my perspective there is that if you look at the advancements in AI architectures, right, over the past 5-6 years, there have been two critical family of advances. One of them is, of course, kind of moving away from traditional SIMD architectures to systolic arrays, right? But that's a Tensor Core or a Google TPU, whatever the case might be. That's one level of architectures. And of course, the second level of architectures is precision scaling, right? So what's happened in the industry is that, of course, there've been architectural innovations in data flows and so on and so forth that NVIDIA has taken on their own perspective, right? They pull it into their chips. And then and of course, NVIDIA is very aggressive about scaling the technology nodes. So even if you have a 2x advantage, you start off with something that is a 2x advantage, but because you are in a backdated technology node, you lose that 2x because NVIDIA has made its chip in 4 nanometers or whatever, right? So my view is the reason none of these startups have succeeded is because the base level of differentiation that you are promising is not high enough over GPUs. It's a factor of 2, it's a factor of 3 over GPUs. And when all is said and done, it's only a factor of 20% over GPUs at best. And this is why I think analog compute is more interesting, because you're starting off with a base that is fundamentally 40x or 20x. So even if you lose 2x in technology node scaling and other innovations, you will still have, at the end of the day, a demonstrable advantage over GPUs. And that's essentially what is, I think, interesting, at least most from my perspective, about analog computing, that the differentiation base is much higher. So even if you lose some because you're in a backdated technology node, you still come out as a winner at the end of the day.
Sounds like an exciting future then.
Yeah, indeed.
Wow, so nice. I feel like we could have this discussion on for hours. So, but we have to move on. So thank you, Kyla, so much for this keynote. We've all enjoyed it very much. We all gained very much good insights. Thank you again for giving this keynote.
Thanks a lot for inviting me.
Thank you very much.
Okay, then let's move on with our next great talk. So it is a talk given by Bernhard Fogginger from University of Dresden. The title is Performance Models and Energy Optimal Mapping of DNNs on Many-Core Hardware with Dynamic Power Management. So it's also my pleasure to introduce Bernhard as well. So Bernhard received a diploma degree in physics from the University of Heidelberg, also in Germany. He is currently pursuing his PhD with the chair of highly parallel VLSI and neuromorphic circuits in Dresden under the supervision of Professor Meyer. He's also a research associate to the chair of highly parallel VLSI and neuromorphic systems of the University of Dresden. His research interests include neuromorphic computing, deep learning, radar signal processing, and he also leads the software development of the Spinnaker neuromorphic hardware. So thank you, Bernhard, for giving this talk here today. So you're on mute, yeah?
Yes, thank you for the introduction, and yeah, let's start right off. Yeah, you already said the name of the title, the Performance Models and Energy Optimal Scheduling of DNNs on Many-Core Hardware with Dynamic Power Management. So what's the challenge, or what's the situation we consider here? Consider whatever, you have a video stream with 30 frames per second, and you have an embedded DNN chip with a limited power or energy budget, yeah, and you have to really do whatever classification or segmentation in this 33 milliseconds or so. And the hardware we have, in our case, we consider the Spinnaker 2 many-core hardware. It has 152 cores, and each of the cores has DVFS, so dynamic voltage and frequency scaling. So we can change the supply voltage and clock frequency of the cores to either speed it up, yeah, so with higher voltage and higher speed, but then consuming more energy, or running it slower at a lower voltage and then to be more energy efficient. So these are the extremes we can switch between. And yeah, the idea is to, or the objective is to find optimal whatever scheduling operation of the system to whatever to match the deadline for processing while being as efficient as possible. So the outline of the presentation is I will first give a hardware description of the hardware we use. Then we have developed performance models for the AI accelerators on the chip, both for time and energy. And then we show some power management concepts, how we could apply for running larger networks on the system by and switching between different performance levels using DBFS. So this is about the Spinnaker 2 many core hardware. This hardware comes more from the neuromorphic community, so neuromorphic computer, brain-inspired computing. You see the chip architecture on the left. It's an advancement from the Spinnaker 1 chip, which has been developed by University of Manchester, Steve Ferber, which is a chip dedicated for the real-time simulation of spiking neural networks. So not dedicated for deep neural networks or DNN inference or so. That's a rather old chip, but in the Human Brain Project, like my chair and Professor Ferber, we worked together to build the second generation, which you see on the left. So it has much more cores. It's 152 cores arranged in this array here. There are always 4 cores in one so-called quad processing element. They share a network on chip router, so there's a network on chip for a high-speed data transfer on the chip and to the DRAM and so on. The core itself, it has an ARM M4 with floating point arithmetic. It has 128 kilobyte of SRAM and a machine learning accelerator with like 64 unit MAC array. So the chip has been fabricated already in 22 nanometer from Global Foundries. So we have it in the lab since beginning of the year, but the results I'm showing here are based on a prototype chip. Let's look at the more detail on the processing element of the Spinnaker 2 chip, which you see here on the right. On the one hand, you see here in this green area, you see really the core logic. So it's the ARM core, and then we have accelerators on the one hand, the multiply accumulate error, but also other accelerators. This part of the PE, this can be operated down to 0.45 volt. This is achieved by using adaptive body biasing, which is possible in this FDSOI approach technology of Global Foundries, and we use IP from our spin-off Ray6 for that. The specialty of this chip is that the PE can select between 2 different supply lanes. So there are 2 global supply lanes, typically between 0.45 and 0.6 volt. And one can dynamically switch which supply lane you want to draw the power from. At the same time, each PE, each processing element, can select its clock frequency by using some dedicated clock dividers. So in the range of 550 to 400 megahertz. And we can switch these performance levels, so which is a combination of the supply lane and the clock frequency, within tens of nanoseconds without stopping the operation of the core. So this is the capabilities we have in changing the supply lanes and the frequency. The other domains, like for the SRAM, that's 0.8 volt, this is fixed, and also for the network on chip, it's fixed at 0.6 volt in this case and cannot be altered. We have an integrated multiply accumulate accelerator, this ML accelerator, so there's not going into detail here, but we have this 16x4 MAC array with int8 operations. You can combine, or the basic operation mode is, so we have a state machine besides that can run either a matrix multiplication or a 2D convolution. The basic principle is that the accelerator on the one hand loads data from the local SRAM and also writes the results back. For example, for 2D convolution, both the input feature maps and the output feature maps, they are stored in the local SRAM, and the weights, they are fetched from through the network on chip, for example, from a remote SRAMs, for example, from the SRAM of another PE or from the external DRAM. So that's the general principle of operation. There's also a post-processing stage here with a ReLU and some quantization to 8, 16, or 32-bit. Yeah. If we look at the chip was originally designed for like spiky neural network simulation, but we added this accelerator, and it takes only 7% of the silicon area of the chip, of the PE, sorry. And this makes the chip quite competitive DNN inference chip with up to more than 2 TOPS per watt. Of course, this is maybe no longer state of the art in academia, but it's at a similar level you can get with commercial products. Yeah. Now let's look at performance models of the Spinnaker 2 machine learning accelerator, both for time and energy. But let me first show how we did the measurements. Yeah, so we have here a measurement setup with a prototype chip, which only contains 8 PEs compared to the 152 of the final chip. What we do is actually, because these we run a 2D convolution in the loop for like 50,000 times or 100,000 times on all PEs. Yeah, and then we measure the power on the different supply lanes. And then we see when the operation starts here that whatever, for example, the SRAM power goes up as well as the compute power here. Yeah. And yeah, and we measure the power, yeah, for all supply lanes. These are the measurements that we do. And then this is the basis for later doing developing performance models. Yeah? We did sweeps of the voltage and the frequencies of the cores. You see here on the left, like the measurement sweep. On the x-axis, you see the clock frequency. On the y-axis, the efficiency for the matrix multiplication, teraops per watt. So the higher, the better, the more energy efficient. And in the different lines, these are different supply voltages. Yeah. We can see, for example, here in the left that the green line with a 0.45 volt, that yeah, the efficiency increases with the clock frequency, but then after 200 megahertz, we have no data point because the calculation is wrong. Yeah, just the transistors are not fast enough to output the right results. Yeah, and then of course the higher voltage you have, the higher clock frequencies you can achieve. Yeah. From this study here, we can identify 2 so-called performance levels, which we consider for further studies. The first one is this performance level 1 at 0.5 volt and 320 megahertz. This has the highest energy efficiency here. So it requires the least energy to complete the task. And the performance level 2, this is just the fastest, which with the highest speed on the chip. Yeah, that's the basis. And now let's go to the concrete models. We developed a time model for running the 2D convolution on the machine accelerator. I'm not going into detail here because I want to save some time. But at the end, it's a gray box model. We did do some fitting after the measurements, and we get an accuracy of whatever less than 9% for the predicted times of the accelerator. More interesting maybe are the energy models. So we have a simple model based on static and dynamic power. So on the one hand, each of the different supply voltages, like for the network on chip, for the accelerator, and for the SRAM, they have some static power, and also there's some static power. And in addition, we have dynamic energy, which we just take as the sum of the energy of atomic actions times the counts, how often they happen. Yeah, this is, for example, an SRAM read access or an SRAM write access, or fetching data through the network on chip, or running the machine learning accelerator 64 Mac unit array for one compute cycle. Then, of course, we know how the accelerator works, so we can calculate the counts for these. We get the time from the time model, and then we can predict the consumed energy when running one layer with some configuration on the hardware. We see here on the right, whatever the breakdown of the energy contributions for three typical layers from convolutional networks. And we also see that here the dynamic power dominates for most of the, for all layers. And the majority of energy is consumed either in the SRAM, but mostly in the core, really, for the calculations. This approach with the atomic actions and energy per action is similar to Accelergy from MIT, but we have an explicit handling of static power, which makes it more flexible, I would say. We can compare the models against the measurement. So we see here again the predicted energy versus the measurements for this performance level 2, which I mentioned before. And we get a very good match here with an accuracy of an errors of less than 5%. For these performance models, we have developed a simple Python package, where you define a model for the execution. For example, here we can fill in the model with fitted parameters. Of course, actually, we wouldn't load this manually here, but we would just save or we do the fitting in the library, save a pickled class, and then restore it. And then for example, we can define the configuration of the 2D layer with the width and height of the input channels, the filter size, and so on. And then we pass this into the model, and we can predict the time and energy for running this layer on this Spinnaker 2 machine learning accelerator. In the next stage, we will use this library to predict the energy and time for larger layers on this Spinnaker 2 system. So it's about power management concepts for energy optimal scheduling of DNNs on Spinnaker 2. So let me first explain the general concept. So the objective is, or let's say we have a network such as VGT16. We want to run it on the Spinnaker system with 152 cores. And we want to do it in an energy optimal fashion. First of all, we have to map and partition the network to run it on this highly parallel system. So, for example, if you look at the largest layer of VGT16, which is this conf12, it has 6 megabyte of input and output feature maps, which is much higher than the 96 kilobyte of the data for SRAM in each processing element. So we really need to split this and parallelize that. In previous work, we have already shown some, the methodology to split layers for that, and also speeding this up through data reuse. Now the dynamic power management that we consider in the study is, so we have 2 performance levels which we can use. These are exactly the 2 that I described before, one for least energy and one for highest speed. And then we say, like for each atomic task, which means calculating a small part of a layer on this on the accelerator, we can choose the performance level, either using the higher one or the lower one. And then we use this to predict the time and energy for running the network on the Spinnaker 2 system. So these are only predicted values here. We haven't tried it yet on the final chip. First, look at the difference between the 2 performance levels. So let's take this worst case, this largest layer from VGT16, and this has to be split into 1024 parts. To run this on the 152 cores, we need to have 6 loops with 152 parts and 1 loop with 112 parts. Running this using the low energy performance level, you see here on the top right, we see here these bars. This is each one loop of 152 cores being active, and only in the last part, only 112 cores are active to compute the remaining parts of the network. Yeah, we see that the power is constant over that time and only decreases in the latest time when some cores are idle. Yeah, and there is this. We can run the same network at the higher performance level with higher speed. So we finish earlier, but have a higher, of course, consume more power. Yeah. So the upper one requires 11% less energy, while the lower one, so the PL2, is 20 times faster. So these are the endpoints where we can trade off our calculation. Yeah. Now let's consider different scenarios. Where could we apply this possibility to switch between a high speed and a low energy mode for processing? Of course, if you want to be as fast as possible, then you just use the performance level 2. If you want to save energy and don't have a time pressure, you could just use the performance level 1, which is more energy efficient. More interesting is this limited time budget setting. So the time is limited, e.g. when frames arrive at 30 frames per second. And then you want to really run this at the lowest power consumption possible. There could be also some limitation by the power, for example, that the power supply unit cannot supply more than a certain amount of power per at a time. But we focus now on limited time. So we first look on a single layer. Again, this layer that we had looked before, so the upper 2 plots are the same as before. And now we consider that the time budget we have is somewhere in between the time finishing with the low energy mode and the time finishing with the high speed mode. So and the time budget we have is in between here. Then we can automatically tune which of the loops is run at which performance level. In this case, the first 4 are run at high speed, and at low energy, sorry, and the last 3 at high speed. And with this, we can save 7.4% compared to the case where we only use the high speed performance level. A similar thing we can do for the whole network. So we consider all convolutional layers here. So it's 13 layers. And again, we consider the case that the time budget is between the time for the low energy and for the high speed performance level. And then in this case, we select for each layer whether it's run at the higher or lower performance level, and we can save 6.6% of energy while hitting the time budget exactly. So that's the thing we can gain with this dynamic power management by switching between these performance levels. Okay, let me come to an end. So to summarize, on the one hand, we've developed simple performance models for this for our accelerator with a decent accuracy suitable for our tasks, and we have developed power management concepts for which is actually transferable to any many core hardware which has some power management capabilities for switching between different DVFS settings. In our case, we can achieve energy savings up to 12%, and that's what we have predicted so far, and what we want to do in the future. It's maybe also interesting. Of course, we want to obtain the performance models for the final Spinnaker 2 chip. We want to extend it to other DNN layers like max pooling, which is run on the ARM core. Consider also data transfer and data alignment, which might be needed. Then, of course, we want to validate our power management concepts on the Spinnaker 2 chip. Try more sophisticated power management concepts, and finally also integrate it into the Spinnaker 2 DNN compiler, which is in development. We are also investigating TVM here, by the way. And yeah, we at the end, what we want to not only do an optimal scheduling, like selecting the performance level, but we also want to create optimal mappings for a combination of that, like choosing splits of layers and that are energy optimal also for the scheduling. And as last, of course, we want to scale up this modeling approach also, because the Spinnaker 2 chip is not only for like embedded systems, but it's a large scale system. There will be server boards with 48 chips and a large scale system with up to 5 million cores to be built up in Dresden in the second half of next year. Okay, that's it for my presentation. I thank you very much for your attention and look forward to your questions.
Wow, Bernhard, thank you very much for the great talk. So let's open up the session for some questions.
Thank you very much, Bernhard. This was a nice talk. Brief question on your slide number 10, you introduce your timing model. Without going too much into detail, can you comment a little bit on why the model sometimes is overly confident, not overly confident, over optimistic in the timing, and sometimes the timing is slower? So it seems to be a quite realistic model in that regard. Can you comment on that? So meaning sometimes the model predicts a faster latency than what you measure, and sometimes it predicts a slower latency. So it seems not to be a worst case or best case scenario.
Yeah, of course. On the one hand, this is here we have we showed a prediction for the same data that we used for the fitting. Yeah, so there will be some balance between whatever overestimating and underestimating, right? The errors, I'm not 100% sure. Yeah, so on the one hand, the data size we used for fitting is not that big. On the other hand, we had some bugs in there in the prototype chip, which like changed a bit how much how long an SRAM access takes. So it's which we not which is not easy to model, at least in here in detail. Yeah, so no, honestly, I cannot explain it right away.
Anyhow, thank you very much for still going a little bit into the detail. I think it was quite a nice presentation. Thank you very much.
Cool, yeah. Can you talk a little bit about the tooling aspect? So I would be interested, how difficult would it be to integrate a new layer and power optimization of a different layer type?
I think it shouldn't be that difficult. So we have the measurement setup available. Yeah, so it would be whatever performing measurements, like developing kind of, we use here kind of gray box models. So we know how the accelerator works. Yeah, so or if we want to run something on the ARM core, then also we know how this scales if we increase some numbers. So I think that's first we have to develop these gray box models, yeah, whatever, and then try to fit them to the data. So I think it's not that difficult actually to add more layer types or so.
Okay, cool. Yeah, what I like a lot is that you actually make energy here not as a given, but that it is part of the optimization space. So as you have shown, you can run multiple models at different energy levels and then exactly meet your deadline. That's quite impressive.
Yeah.
Cool. So I think we have time for one more question. Okay, then we're good. So all clear. So thanks a lot, Bernhard. It was a great talk. It was a pleasure having you here.
Yeah, thanks.
Okay. So up next is a talk about network architecture search. So the title is high TNAS hybrid transformer neural architecture search for edge devices. So the author or the presenter is Lofty Abdelkarim Mehabad. So my apologies if I have butchered your name too much. So hopefully this was kind of the right pronunciation. So let me introduce him. It's my pleasure. So Mehabad is currently a graduate student in computer science from the École Nationale Informatique from Algeria. And he has joined a university, Polytechnique, Hauts-de-France, as a research intern this year, under the supervision of Professor Nia Ismail. His research interests are computer vision, AutoML, and edge computing. So Lofty, please give it away.
Hello, everyone. Can you clearly hear me?
Yes.
Okay, perfect. So I will share my screen. I think you are able to see the screen
Yes,
right now.
you can see
Okay.
it perfectly fine.
I can start.
Sure, go ahead.
Right. So hello, everyone. Thank you for having me here. My name is Mesharbat Lotfi, and I am a student at recently graduate student from École Supérieure d'Informatique Algeria. I'm glad to be here today to present you our work, High TNAS Hybrid Transformer Neural Architecture Search for Edge Devices, which I have done as part of my internship in LAMI laboratory in my final year of my master studies. So vision is crucial in our interactions with the world. We as human beings accomplish daily tasks such as detecting and classifying objects around us. The field that aims to automate this type of tasks is known as visual object recognition. It consists of identifying and localizing objects present in an image. It has a wide variety of applications such as autonomous vehicles and tumor detection in healthcare domain. Currently, the dominant approach in this type of tasks is deep learning. Deep learning models are known to have high accuracy in various fields, including object recognition. They are also extremely flexible due to the wide variety of hyperparameters that control them. However, they have high computational and memory complexity. As we can see here, this complexity is continuously increasing over the years. This is why usually these models are deployed on the cloud. The data is sent from the source to dedicated servers on the cloud where the model is executed, and then the prediction is sent back, as you can see here. This process, however, is unreliable. It depends on network quality. It is slow, especially for real-time applications, and it's not suitable for critical applications such as in the healthcare domain. This is why Edge AI is emerging in recent years, where DL models where deep learning models are executed in edge devices that are put near the data source. So we have more reliable execution, no data transfer over the network, and we preserve the confidentiality of our data. However, this the edge AI faces many challenges due to the fact that deep learning models are known to have gigantic architectures. They are too big to fit in edge devices. Also, they are huge in terms of computational complexity, and thus they are not fast enough for inference in edge. And they have high power consumption that drains limited power source for edge devices. We can see here that a lot of deep learning models are above the edge limit in terms of the size, number of parameters, and almost all of them are above the tiny limit. This is go to our work, which aim to make deep learning models more adapted to the context of edge. One way to do so is by hyperparameter optimization. Hyperparameters allow us to control the performance of a deep learning model. Hyperparameters allow us to control the performance of a deep learning model. However, tuning hyperparameters is a difficult task, especially for us as humans, due to many reasons, such as that the space of possible configurations is of immense size. If we have, for example, a typical architecture where we have 4 blocks of deep learning operations, if we tune 5 hyperparameters per block, we end up with a size close to 10 of power of 12, which is a big search space that we cannot explore manually. Secondly, we have a high cost evaluation because it consists of training deep learning architectures. For example, the learning time of Vision Transformer or ImageNet 1K on 8 NVIDIA GPUs is 65 hours according to Facebook. This is why in our work we aim to propose a new automatic search method to find hybrid transformer models that are fast, deployable on small edge devices, and effective for visual object recognition. We choose 2 main tasks for our target, which are image classification and object detection. And our goal is to bring down the deep learning model under the tiny limit. This type of automatic search for deep learning models is known under the name of hardware awareness. Hardware awareness models, hardware awareness methods try to solve the multi-objective optimization problem that consists of searching for models that are both accurate on the target tasks and efficient according to hardware metrics such as latency and energy consumption. To do so, hardware awareness techniques uses 3 main components. First, a search space that define the possible configurations to explore. In visual object recognition, we have 3 types of emerging or 3 types of architectures, emerging architectures. First, convolution neural networks that are based on the convolution operations. They are widely adopted, especially in the image context. Second, we have the vision transformers. They are based on the operation of attention, and they are recently adapted to the image context. They are known to have higher accuracy than convolution neural networks, but they are more complex in terms of computation and memory. And third, we have hybrid models that contains both attention and convolution blocks, and they try to combine the best of the 2 worlds. The second component is the search strategy. It determines how to explore our search space. Mainly have 2 types of methods: compute-based, such as the evolutionary algorithm NAZIA2, and model-based strategies such as multi-objective Bayesian optimization, which relies on 2 main components. First, a surrogate probabilistic model that tries to estimate the objective, and an acquisition function that determines the next solutions to explore. Our third component in the hardware awareness is the evaluation strategy. It determines how to get the objective of a given architecture or the performance of a given architecture. This phase can be very costly That's why a lot of techniques have been used to reduce the cost, such as reducing the training cost, using prediction models instead of calculating the actual objectives, use one-shot methods that train a single model of the search space and try to extract subnetworks from it, and zero-shot methods that use a numerical score as a proxy for the accuracy of the neural networks. In our work, we introduced a new hybrid search space. We also developed a new search strategy based on multi-objective Bayesian optimization that aim to accelerate the convergence of this type of methods. And we have used as an evaluation strategy prediction models. In the next slide, we will discover more details about our method. First, we have the hybrid search space. To construct our search space, we first proposed an initial search space based on the state-of-the-art architecture for visual object recognition. But the search space was too big to efficiently explore, and it does not consider hardware constraints, which is our objective. That's why we have done an efficiency analysis of this for initial search space, where we have done a comparative study of the efficiency of state-of-the-art models and operations on edge devices according to hardware metrics, which are latency and memory consumption, essentially. We have deployed this state-of-the-art models on two types of hardware, as we can see here, CPU and Jetson Nano. And we have calculated their latency and memory consumption. We reported also the accuracy here. From this analysis, efficiency analysis, we came out with two main conclusions. First, that hybrid models are more likely to be deployed in edge devices. And the second is that hyperparameters such as the number of heads and the embedding size have more impact on the size and efficiency of the model than others. Based on these results and inspired by mobile VET, we introduced a search space shown here. First, we have two convolution blocks followed by 3 attention blocks. And for each block, we varied these hyperparameters. To evaluate, to ensure the efficiency of our hybrid search space, we sampled the architecture randomly from it and measured its performance or their performance. The results show that our search space contains both fast and and accurate models for visual wake words. So we can assure that our search space is effective. Also, to explore the search space based on accuracy, speed, and also considering the number of parameters, which is a decisive metric in determining whether deep learning models are deployable on edge devices, we proposed a new search strategy based on multi-objective Bayesian optimization that followed the following process. First, we initialize architectures from our search space and evaluate their performance. As you can see here, we calculate the accuracy and latency. Second, we fit a set of surrogate predictors, probabilistic surrogate predictors, on all the data that we have constructed earlier. And we obtain the mean and standard deviation here, trying to estimate our objectives. Third, we assign a score to each probable observation based on its likelihood of helping the optimization process to improve the current solutions. We end up with an acquisition function for each objective that determines as I said, the likelihood of helping the optimization process to improve the current solution. We optimize these set of acquisition functions through using a multi-objective solvers. We use NHCA2 here. After optimize it, we obtain a Pareto front. We select from it the best solution based on the hypervolume improvement metric. and we repeat the process. To construct this method, we varied multiple components in the multi-objective optimization process, mainly the surrogate model, the acquisition function, the multi-objective solver, and selection method. The result shows that using XGBoost as a surrogate and upper confidence bound as an acquisition function, also NSGA2 as a multi-objective solver, and hypervolume improvement as a selection method, gives us the best result or the best average number of discovered Paretos in the tested benchmark. To evaluate our search strategy, we compare it to other search strategies, which are random search, NSGA2, and standard multi-objective optimization. We first we calculate the the improvement of hypervolume according to the number of evaluations. We can see that our method converges faster by obtaining a higher hypervolume with fewer number of evaluations, as we can see here in the green line. We have also plot the solution obtained by each of these methods, the Pareto front obtained by each method, and we can clearly see that our method obtained better results by discovering a more optimal Pareto front. After developing and tuning each component of our hardware awareness strategy, we combine them together in order to test them on the target tasks, which is first visual wake words, which aim at determining whether a person is present in an image or not. We have tested these models on visual wake words benchmark. We compare our resulted models shows in gray with state-of-the-art models, which are mobile VET, mobile net, and proxyless NAS. We can see that our best latency model, shown in here, outperformed the variants of mobile VET, while significantly reducing the latency and number of parameters. We can also see that our best accuracy model shown here is largely more accurate than all the other state-of-the-art models, while having lower latency and being also smaller than the most of the state-of-the-art models. Also, our best model in terms of the model that gives us the best trade-off in terms of accuracy and latency surpasses the 90% accuracy in visual wake word dataset benchmark, with the latency and size more optimal than all the others. We have also tested our method on person detection, which aims at identifying and localizing persons present in an image. We obtain a detector that achieves better accuracy than mobile net V3 while being 5 times more smaller. And also it achieves similar accuracy to the smaller version of mobile VET while being 2.8 smaller. So to summarize our work, we proposed a new method for automatic search of neural architectures adapted to the hardware called HiTNAS. To do so, we realized a comprehensive study of vision transformer models for visual object recognition on several hardware platforms. We then proposed a new hybrid search space that includes convolution and attention blocks targeting small edge devices. And in the end, we propose also a new search strategy aims to accelerate convergence by finding good architectures in a relatively small number of evaluations. We accomplished our goal, which was to bring down the size, bring down the deep learning models under the tiny limit by using our method. For the future, we aim to expand our search space by allowing interchanging of attention and convolution blocks. We also consider we also want to consider other metrics in the optimization process, such as the energy consumption. And we want to expand to more use cases, such as semantic segmentation. So thank you for your attention.
Wow, amazing. Thank you for your great talk.
Thank you for having me.
So let's open the session for questions. Anybody in the audience who wants to ask the first question? Daniel, please go ahead.
Okay, yeah, thanks also for a nice talk. And I would have two questions. So the first question I would have, I think you choose NSGA2 as the search heuristic, right? The genetic algorithm. There I would be curious why you choose this one, and if you also tried out others, because I know there are also some search heuristics, for example, which try to be kind of quasi-gradient based. For NAS, have you tried them out, or was your focus more like on stochastic methods like genetic algorithms?
Yes, we focused on compute-based algorithms because we don't have access to the gradients. We can use gradient-based algorithms. And here, NSGA2, we use it to optimize, as we can see here in the search process, we use it to optimize the acquisition function. Acquisition function, the number of, the cost of a single evaluation for the acquisition function is really low. That's why we can run NSGA2 for many trials, and we can obtain good results using NSGA2. That's why we focused on compute-based search strategies. We haven't tried out other methods, really.
Mm-hmm. Okay. Can I ask a second question?
Yes, of course.
What I was also wondering is, in a lot of like machine learning tasks, there are now standards, or some tools are becoming the quasi-standard, right? For the NAS, I don't see this. As a NAS, I see like lots of groups, and each one has its different network architecture search tool. Do you see that, or do you see there's some possibility, or do you think at some point like it would be rather, you know, some open source projects where then all the groups are contributing their algorithms, or is this NAS so special that kind of everybody needs a tailored solution?
Yes, I think that it comes from the fact that NAS is applied on a wide variety of tasks. They are very different. They can be very different. For example, if we change the search space, it's impossible, for example, to compare two neural architecture search methods that use different search spaces. So I think it came from the fact that neural architecture search is used everywhere, and it's hard really to standardize like or come out with some benchmarks that can really compare these methods.
Okay. Thank you very much.
Thank you.
So, anybody else?
Another question, if I may. Very nice talk. I liked it very much. I appreciate your time. A question on the comparison against the random search. Can you comment a little bit on when you compared your search process against others? Something I noticed from the graph here is that you improve, or you ultimately find a hypervolume which is much larger than anything you find with the others. To me, this, well, can you comment a little bit on the maybe diversity of the search space, or why there is such a large gap?
Yes. First, our goal is like to improve fast conversions. From the beginning, our goal from this, our objective from this search strategy was to improve the hypervolume, because as we said, the evaluations are really costly, and thus we urgently need, or we need to have fewer evaluations and obtain good results. especially in our case where we didn't have access to compute, to really powerful compute platforms. So the gap, I guess, because it's mainly, if we can see here, yes, with the average number of discovered Paretos, we can see here that is the combination of those methods, those components that allow us to have this higher gap in comparing to random search, as we can see here. So I guess it's the parametric test that we have done that allow us to have this gap in terms of hypervalue.
Okay, can you, so as a follow-up question, thank you for that clarification, but maybe you can comment a little bit on if you expect when you run, for example, NSGA2, if you run it for a longer time, would you expect then this gap to be closed at some point, or is the search space too large to ever really close that gap?
Yeah, this is an interesting question. I think it depends on the search size, but I think NSGA2, after like enough number of evaluations, the gap will eventually close between the two. But as I said earlier, our goal was to obtain fast conversions, and thus we focus on obtaining a good or better Pareto front in fewer number of evaluations. This is why we didn't really focus on running the methods for longer or larger number of evaluations.
Yeah, understood. Yeah, impressive work. Thank you very much. Liked it a lot.
Thank you.
Okay, good. Then let's close this session and thank you again.
Thank you for having me. Thank you.
All right. Now, following up, our next speaker is Andrew Roche. Sadly, he couldn't join us live today, but he was kind enough to provide a video for us that we will now play to you. And one of his colleagues was volunteered to answer questions in the Q&A session. Andrew is going to talk about whole model optimization in Apache TVM. And Andrew is a software engineer at OctoML and has been involved with Apache TVM for 2 years now. He's an Apache TVM committer and member of the project management committee. He leads the efforts around micro TVM, both at OctoML and at TVM in a more broad sense. Prior to OctoML, he worked on digital IC design on embedded firmware for medical devices at Verily. Andrew holds a Bachelor's of Engineering in Computer Engineering from the University of Washington. Now, Michael, please.
Hi, everyone. My name is Andrew Roche. I'm a software engineer in OctoML, and I'm also a member of Apache TVM's project management committee. And today I'd like to talk to you a little bit about whole model optimization with Apache TVM. So let's get started. So I'd like to open with a challenge that's kind of near and dear to many of our hearts, which is deploying this simple CNN here onto a tiny SoC, such as the one shown here.
See your screen. We just see.
Why is this hard?
Pardon me?
We only have a black screen. We hear the sound, but we don't have the screen.
Not true. I could see it.
Yeah, I could see it too.
Okay, then sorry, then carry on. Then it's a problem on my end.
Well, to be blunt, tiny SoCs are tiny. Less memory means we have to be very judicious about how we use it. Slower CPUs means we have to care a lot about performance. And power constraints mean that on top of all of that, we have to think a lot about battery life. And while there are minimalist Pythons that run on these tiny ML SoCs, if you try to stack a giant hulking ML stack like TensorFlow's x86 interpreter or PyTorch on top, you're going to have a bad time. So to describe the challenge a little bit further, what is it we want here? Well, we want a way, ideally a tool, that could translate models from these popular deep learning frameworks into a library that was small, fast, and accurate, so we could run it onto on a tiny device. So let's start with a simple approach. Just for a second, what if we let someone else deal with the fast, small, accurate problem? In other words, as I'll use in this example here for ARM architectures. Well, if we had this library, then we could just build a tool that walks through a deep learning model's layers and maps each layer into a call into one of the optimized library's functions. And this works pretty well for a single core system, but microcontrollers are quickly becoming much more than single core systems. Already common today are microcontrollers with multiple CPUs, but coming soon are heterogeneous compute architectures where accelerators and CPUs can work together to achieve faster inference. Now, our simple approaches got a lot more complicated because now we have two libraries to deal with. And at each layer of the model, we need to make a decision. Which library should we use? This question is a little bit more complicated than just comparing the two libraries side by side, because at each layer, the size of the layer might actually change the calculus here. In other words, a smaller layer might perform better on a CPU and a larger layer might perform better on an accelerator. There are also architectural constraints to think about. For example, some accelerators can only operate out of smaller SRAMs that maybe can't fit all layers. So it's not just sort of a one-size-fits-all strategy here. It might not be worth it to copy the workload from the main memory into the accelerator SRAM just so you can run the accelerator. And failing that, you might ask, well, maybe we can use a second CPU to speed up your workflow and the workflow in parallel, but is that faster? So how can we build a tool that can help us to surmount these challenges? When we start thinking about things like this, we start wanting to know things like, do we have a model of the system architecture? Do we know how tensors are represented in the underlying RAM? And what's the overall structure of the implemented program? At this point, we're starting to ask questions that are better answered in a full-blown compiler. And for that, I present Apache TVM, which is an open source deep learning compiler. TVM accepts models defined in popular deep learning frameworks like the one shown above, and it compiles them into optimized implementations that can be run across a wide array of devices. The range of devices ranges from large data center CPUs and GPUs all the way down to the tiny ML SoCs that we saw at the beginning of this presentation. The TVM has been around for a little while. It actually just turned 5 this year, and it has over 750 contributions from both industry and academia alike. It's used around the industry at companies that are fairly well known. And at the most recent TVM user conference this past December, we had over 700 attendees. So now that I've introduced TVM to you, I'd like to talk a little bit about micro-TVM, which is a sub-project within the TVM project that aims to leverage TVM to run models on bare metal devices. Micro-TVM works in places that don't have operating systems, doesn't require any virtual memory, it doesn't require malloc, and it doesn't require any advanced programming languages, although you can use them with micro-TVM if you want to. Micro-TVM is aiming to help codify and automate the process of taking a model and deploying it onto any hardware target while taking into account the type of hardware available, the constraints of the individual application, and the model being deployed. And what this means is finding a way to build languages that describe these problems, and then finding a way to integrate those languages into a tool and define well understood transitions between them. So let's see how micro-TVM implements a model in C, just to see what we get out kind of at the end of this process. We'll start with the top level main function. And you can see this looks kind of familiar to our previous example. It's a set of calls to optimize layers. These could be calls into an off-the-shelf library like CMSysNN, but TVM can also generate its own optimized implementations for just about any hardware that micro-TVM can run on. And more importantly, this top level main function is plain old C. Any firmware engineer can inspect, modify, and debug it to see what's going on. Looking at the operator functions themselves, let's just say these are the native operator functions, they're the same way. It's plain old C that you can inspect, modify, and debug. So let's talk about how we get there from a model. In phase 1, TVM will import a model from a deep learning framework into its own native language called Relay. Relay is a graph level or model level language that aims to canonicalize any sort of nuances between the two frameworks, or between the various deep learning frameworks. So for example, if TensorFlow sort of automatically attaches an activation function to convolution, we can represent those two things separately in Relay. By the same token, if Onyx encodes dequantization information, we can also represent that in Relay in a canonical format. Once we've imported a model into Relay, we then move on to an optimization step. And this happens partially in Relay, partially in Tier. But it centers around a step called scheduling, which translates the Relay module in chunks into an imperative language called Tier. Now, Tier is kind of like C, but it also includes higher order things like memory management. And you can reference this to Relay. So for example, in this Tier module that I'm showing on screen here, you can see things like for loops, array accesses, arithmetic, as well as just simple assignments here. So you can see how this is lowered into C. And speaking of which, the final phase is to then take that Tier and hand it off to a code generator that knows how to translate it into a format that's appropriate to the final hardware, to the hardware that we're targeting. So here we're showing C source code generation, but you could also hand this to LLVM to do direct binary assembly code generation, or any other binary format you might need with your accelerator. Now I want to zero in for a second on Tier, because we added a new thing into the equation here. Why even bother with Tier? A simpler approach, like the one we talked about before, was to go straight from Relay down to this C or LLVM implementation. The first reason here is that it allows TVM to split apart the problems of model parsing and implementation. But the real power of Tier comes in that it allows TVM to define procedural optimizations over the model that are agnostic to the output language. So for example, the same common sub-expression elimination pass can be used on GPUs, on CPUs, or in situations where other accelerators are involved. And more interestingly, TVM can leverage this Tier representation to perform common optimizations such as tiling, loop reordering, and vectorization or tensorization automatically by learning which is best for your target. So now that we've talked a little bit about Tier, let's focus in on optimization, which is what I came to talk about today. And today, as I mentioned, optimization kind of happens in both Relay and Tier, but it's kind of split between these two worlds. The graph level or model level optimizations are most often done in Relay, while the operator level implementation optimizations occur in Tier. And there are a few places in the compiler with joint visibility over the two. As an example, let's take operator fusion in TVM, which today operates in Relay. Because we don't have any information about how each of the operators in this particular program are implemented, you can see here we have a convolution followed by a broadcast add and a rail U activation. You have to use this kind of model level approach. So what we'll do is we'll label each operator with enough information to kind of know how it could be fused. And this assumes that we know something about the way that the model that the operator is going to be implemented. We then run a generic fusion algorithm, which groups the labeled operators based on rules about this, this operator kind. Lastly, we express this grouping in Relay using closures. This pretty much wraps up the operator fusion pass in Relay, and we hand the results off to a scheduler to go and implement the blocks of fused operators in Tier and imperative implementations. And all of this works fine as long as the operator implementations obey the labels applied here. So what can we not do with an approach like this? Well, what if we care about the implementation of an operator when we are deciding whether or not to fuse it? For example, what if we only want to fuse things in based on certain loop structures? What if we want to look at the way that a tensor type is actually represented in memory when deciding whether or not we care to fuse it? Or what if we want to look at the whole program to see how much memory is actually available at any given time when deciding to fuse? We don't have this information in Relay, and Tier is too low level to express this graph, express the model graph. So to solve that problem, I'd like to introduce Relax, which is a new Relay-inspired graph level IR. Relax has been developed in the open source alongside TVM, and it brings language improvements around dynamic shape support, blending third-party libraries, as well as brings sort of an iterative, interactive compilation process that we'll get to in a little bit here. Now, I do want to say that Relax has been written by my colleagues and others connected to the TVM community. It's not my work. Here I'm presenting it to show you how I think it will be relevant in a TinyML context. So one of the first things I wanted to talk about with Relax is coexistence. And we've talked a lot about how previously and currently, I guess, in TVM, the graph level representation of a model lives separately from the way that the operator is actually implemented. In Relax, they can actually live together in the same code module. So here, for example, we have the graph level representation, and alongside that, we have the operator implemented below. Now, any given optimization pass can reference and modify the whole program if it wants to. So let's apply this to that fusion problem that I just posed from before. The relaxed fusion strategy is a bit more straightforward and compositional. First, we just decide which layers we want to fuse. And since we can look at the implementations, we can use kind of whatever we want to in order to motivate that decision. Let's say we decide to fuse the layers according to this pattern here. Then we extract the layers we want to fuse into a separate relax function, and then pass it along to the canonical relax compilation pipeline, which will then go lower the relax function into a tier and fuse the implementations together. And here you can see that the add and the exponentiation operation are fused into the same output. What changed here from our previous approach? Well, we have a lot more information available to help inform our decision. As I discussed, we can look at all the implementations to see what's to understand how they're currently made and make that decision about what to fuse, either as a user-facing decision, as a accelerator-specific heuristic optimization, or we can even still use the pattern-based method from before. But we can also explore some other possibilities here. For example, we can fuse based on the available memory. Maybe we want to debug a fused operator block, and we'd like to ideally split things apart if there's memory to spare. Now we can do a whole program memory analysis and figure out whether or not we actually have the memory to split apart a ReLU from a convolution operation, for example. And I should say this also extends to the dequantized operators, which may cast these to a smaller data type. Or requantization operators. We can also fuse complex operations together. For example, we can take two convolution 2D operators and we can stripe them if we want to. Lastly, on micro-TVM, this allows us to tensorize the requantization operators, which lets us leverage SIMD instructions to handle these broadcast multiply shift operators. Okay, so that's kind of our fusion example. I wanted to talk about some other features of Relax that are also very interesting and coming to TinyML. The first one is dynamic shapes. So Relay at this point has had mostly static shapes, particularly for TinyML applications. But in Relax, you can actually use variables to form constraints in shape expressions. So here we're showing an example where we constrain one tensor and then we apply an operator to it, and the shape of the output tensor is defined by the shape of the input tensor. Relax also makes it easier to integrate third-party code. So previously, we had to jump through a whole bunch of hoops to teach TVM about a custom library. Now it's a matter of just writing a single line in Relax. And lastly, it's easier to try out optimizations. With this natural Python interface we call TVM script, you can actually hand optimize your whole model through an intuitive Python interface like the one shown below. So where is Relax now? Well, today it's been prototyped a long time alongside TVM in a fork. And now it's being proposed to merge in TVM's mainline. It's still early days for Relax, but the project would love to get feedback from early adopters. It'll be a few more months before we can leverage these techniques on TinyML devices, even in the prototype, but work is actively ongoing to change that. And given that we expect this to be broadly applicable to optimizations for heterogeneous architectures, we wanted to highlight it here today. I wanted to wrap up with a slide about getting involved. As I mentioned, TVM is open source. MicroTVM and Relax are all community-driven efforts, and we welcome new contributors to come check out our projects, open pull requests, talk to us on the Discuss forum. I've included a link here where Relax has been incubating, so you can check that out if you want to. Also, we have a weekly community meeting that I invite everyone in the audience to attend. You can find all of these links at this community page in the big link at the bottom of this slide. Lastly, I'd be remiss if I didn't mention that I work for OctoML, and OctoML is hiring. So if any of this interests you, please check out our careers page or do send me an email. I'm happy to connect you with the right people. With that, I'd like to say thank you. And I'd like to again note that much of the work that I talked about today, in particular Relax, was authored and contributed by members of the TVM community. Just like to thank them for all of their hard work here. With that, I'll take questions.
Yeah, I hope you all enjoyed the video we have. As I said, sadly, Andrew couldn't join us, but his colleague and fellow TVM contributor, Tian He, volunteered to answer questions on his behalf. So please, if you have any questions about Andrew's talk and TVM in general, come forward and ask them. Welcome, by the way.
So I will have one question. Hi, thanks. I'm really thrilled by the relaxed language and all the implications and the new features. So it's really everything that that we have been looking for. What was a little bit more difficult in Relay. So one of the questions I have, what is the current status of the front end? So if I have a neural network in PyTorch, TensorFlow, or whatever, is it already possible to bring it into a Relax representation?
That's a great question. So right now, Relax is still focused on vertical, right? Which means that the current development community it's not getting to a state where you want to do like all the platforms and all the kind of models. This being said, there are efforts on, for example, Relay to Relax translators, so that allows you to leverage existing front end. And then there are also planned effort on adding like a specific front end that brings in, for example, PyTorch models directly onto the Relax representation. So as of now, it's still kind of work in progress. But if you are looking for, say, a specific model, there's already flows that allows you to do a bit of a customization and bring it into Relax. Yeah.
Cool. Thanks.
There's no one else. I actually have a question. So how about the integration of Relax and also the meta scheduler, which is like also the other big feature that is worked on in TVM. So is their integration going to be a bit more smooth in the future than?
Exactly. Actually, when we design Relax, meta schedule is already out. So we kind of designed with meta schedule in mind. Specifically, previously when we do like meta schedule in Relay, actually we have to do a lot of hacks to be able to intercept compilation, and also meta schedule sometimes we want to have a post scheduling writing of data layout. So for example, if you do looping this way, you want to have your weight to be reordered to that way. And previously that was done by a hack, which we kind of need to hack into the convolution operators to be able to specify that, hey, you need to do this. But in Relax, actually, it becomes very easy. So it everything modularizes into a IR module to IR module path. It was not possible before because like meta scheduling decision kind of sits on the boundaries of high-level computational op and the low-level tensor IR op. But because Relax allows us to represent both, so effectively that decision also become a path, and we no longer have to do all the hacks that we need to do in Relay. Yeah.
Awesome, great.
So regarding the dynamic shapes, this is a very, very interesting feature. So are there any restrictions that you're aware of? So is it possible to do activations, weights, is something like conditional shapes possible, or do you see any restrictions at the moment?
So the dynamic shape design, I think the key highlights is we leverage a symbolic shape capabilities, right, in TVM, which kind of already exist in the tensor IR level, except that we're kind of bringing in the first classes in a computational graph. So, well, our goal is to have broad coverage, which means that you will be able to represent and run any dynamic shape workloads when possible. However, the way you compile them can be very different. For example, if you're like very dynamic, you know nothing about the things, you kind of need to dispatch them onto runtime libraries that don't have any optimization, right? But on the other hand, in a lot of cases, we realize that actually there's a niche intermediate ground where that, for example, all the batches are the same symbolic shape, right? We can leverage that property. Or we know that, say if you take a tensor, you flatten it, the original tensor is n by m, and the flattened tensor is n times m. So through symbolic shape proof, we will be able to prove that these two tensors memory size is equal to each other. So we will be able to do some more advanced optimizations in here. So the answer is yes, we'll try to design for coverage, which means I want to support as many as possible. But also introduce symbolic shape capabilities that allows us to be able to, do things in a more informed fashion. So you can have like advanced dynamic shape optimization that wasn't possible before. Yeah.
Cool.
Will this then also support things like non-rectangular shapes, like triangular data, for example?
That's a great question. So as of now, the Relax design, I would say it's compatible, which means that because Relax have this concept called object, which means that not only you can support standard tensors, you can introduce a new data type called triangular tensor, right? And you perform special optimization for that. But this being said, it's only infrastructure level support. There's no concrete implementation for triangular tensors yet. Yeah.
Okay, great.
I have a question if there is time. So I've also been working with TVM, so I found this feature extremely interesting. And my question is, I have been working with auto TVM and the auto tuning of the TAR and so on. And now if we are fusioning different operators together, here we are talking about another new search space where we can select different manners to fusion them and how to deploy them to different heterogeneous devices when they are available. So are you thinking about this kind of new search space definition and so on?
That is a great question, right? So one of the goals that we do here, at least as about TVM and more recently this push of TVM Unity, right, having relaxed meta schedule, it's not necessarily for us to solve all the problems together. Actually, we want to be able to provide a good set of foundations so that we will be able to solve new problems. For example, now auto scheduling becomes a path, right? That means that you can easily say that, hey, I'm interested in this convolution fusion. Let me try to just take that out. Meta schedule is a probabilistic language that allows you to actually write new search space when necessary. So you will be able to use meta schedule to write that, run that, right? But then on the rest of the cases, let's use the original TVM pipeline, so I don't have to worry about the other parts, right? So this kind of compositionality is what really want to enable. So like you said, indeed, there will be questions like how do we design new search space and so on. But this kind of new compositionality allows us to be able to explore these ideas much faster without having to, fork TVM and redo everything from scratch. Yeah.
Excellent. I guess we will talk a lot in the future then.
Okay, thank you very much for your questions, and thank you very much for your time to answer those questions. If you have more questions about TVM, stick around. Chang-Hee will be back on his keynote starting at 7 p.m. But before that, we have another talk by Philip van Kempen. He talks about ML on MCU, tiny ML benchmarking with fast retargeting. So Philip is a PhD student at the chair of electronic design automation at Technical University in Munich, where he also received his bachelor and master's degree in electrical engineering. In his research group, they are solving challenges related to top extreme edge AI applications or tiny ML, and apply virtual prototyping models for tasks like safety analysis, and focusing their research on the RISC-V targets. And this includes optimizations at several stages of the design process, so training, hardware design, and at neural architecture search. And yeah, Philip, take it away.
Okay, can you see my screen?
Yes.
Okay, then I can get started. Okay, welcome to my talk about ML and MCU, our tiny ML benchmarking tool with fast retargeting. I'm Philip van Kempen, and I'm going to skip this slide because I was already introduced a moment ago. This presentation is structured into 4 parts, starting with a short introduction before I briefly introduce some implementational details. This is followed by 2 experiments conducted with ML and MCU and a short conclusion. Tiny ML is a field where we try to run machine learning tasks on very small edge devices, which always involves several resource constraints. And while on-device training is getting more popular right now, the following only considers inference applications. Further challenges we have to deal with are the use deployment method and the hardware design. Benchmarking and virtual prototyping should help in this decisioning process. However, the number of different combinations of hardware architectures and machine learning frameworks is pretty huge right now. Thus, we propose ML and MCU, a framework-independent deployment and benchmarking tool with fast retargeting support. Currently, there are 2 large frameworks for TinyML inference available: TensorFlow Lite for microcontrollers and the deep learning compiler suite, TVM. TF-Lite Micro, which can be seen as the industry standard right now, offers a set of hard-coded reference kernel implementations, which can also be replaced by optimized vendor libraries. My colleagues proposed a tool called TF-Lite Microcompiler in the past, which allows static code generation for TF-Lite micro models. TVM, on the other hand, as mentioned in the previous talk, follows a compiler-driven approach, generating the kernel implementations automatically in a target-optimized manner. MicroTVM is a sub-project of the framework supporting deployment on bare metal devices, such as microcontrollers. The key design principles before and during the implementation of ML and MCU have been isolation, reproducibility, parallelism, and extensibility. The project is structured in the 3 main modules: configuration, flow, and evaluate. Where the configuration and the evaluate model focus mainly on management-related code, for example, to install dependencies and export specific results. This flow module can be seen as the heart of the project, which is why the following slides will focus on this module. We define a set of stages here, which can be used during a benchmark. In the following, I'm going to introduce the component types supported by ML and MCU. And also, I'm going to mention in which stages in the flow they will be invoked. First, you provide a model either by name or path, which is loaded then by ML and MCU using an automatically chosen front end. ML and MCU also comes with a set of supported frameworks, and for each of those frameworks, 1 or more backends are provided for the code generation of the model inference code and the kernels. In an optional stage, the model can also be tuned for a given target. Next, the generated code is used to compile our targets of the binary, which is then executed and monitored on a target device or simulator. The generated matrix or artifacts from previous stages can then be further processed, for example, to create extensive visualizations or do some filtering. Features are a special type of component as they allow altering the behavior of specific components, for example, by adding callbacks and modifying their configuration. As a sneak peek for the following experiments, I would like to show you the commands I have executed to generate the raw data for these benchmarks, only using the ML and MCU command line interface. In addition to this interface, there also exists the Python development API for ML and MCU. Before starting with the actual experiments, I want to introduce our methodology briefly. The 4 used models are taken from the MLPerf Tiny benchmarking suite in their quantized form. 3 of them are depth-wise separable or normal convolutional neural networks, while the anomaly detection one is just a simple DNN. Later, we are going to compare the performance of TVM on 4 different hardware targets to learn how the framework can adapt to the microarchitectural differences. Be aware that all of these are running at different clock speeds. Thus, their usefulness and the absolute performance should not be the point of discussion here. As all these boards come with a relatively large flash memory, most likely only the SRAM is going to be a limiting factor in some cases. This brings us to experiment A, where we first want to compare the 2 TF-Lite micro backends supported by ML and MCU. Then we do the same for 3 of the supported TVM backends before comparing the frameworks themselves against each other. For the sake of simplicity, This experiment was done on our own instruction set simulator instead of real hardware. The considered metrics here are cycle or instruction counts and the memory usage in terms of ROM and RAM given in kilobytes. Yes. Here you can see all the generated metrics, but let's have a look at it chunk by chunk. In this column, you can see the generated metrics for the backend TF-LMI, which is based on the default interpreter-based runtime of TF-Lite Micro. While in the other column, you can see the metrics obtained using our custom TF-Lite Micro compiler. You can see that while we can get rid of most of the inference, most of the initialization or setup overhead, the measured inference time to invoke our models stays exactly the same, which is expected because we are iterating over the same kernels in the end. On the other hand, looking at the memory overheads, we can see that using our TF-Lite microcompiler, a good reduction in ROM usage, so code size, as well as RAM usage can be achieved, making the TF-Lite microcompiler superior over the default interpreter-based runtime. The three TVM backends considered here are the ahead-of-time compiler, without and with the recently implemented memory planner called USMP, as well as TVM-RT, which is based on the nowadays kind of legacy JSON-based graph runtime in micro-TVM. This runtime introduces major overheads, making it unsuitable for most applications. While TVM-AOT and TVM-AOT Plus perform very similar, we can see that due to the improved memory planning algorithms in TVM-AOT Plus, and an improvement in terms of RAM usage can be achieved of up to 28% in these benchmarks. Now let's compare each framework's best performing backend with each other. It can be seen that the default reference kernels in TF-Lite Micro cannot keep up with the inference performance of TVM-generated models. While for all the considered memory-related metrics, TF-Lite Micro outperforms TVM, often even by a factor of 2. This is partly caused by some legalization passes in TVM, upcasting all 8-bit tensors to 16-bit, which have to be manually disabled to deal with this issue in the future. We have seen that the interpreter-less backends are superior against the alternatives. However, I would like to mention that while the graph runtime introduces several one-time overheads, it is still a very useful tool, for example, for debugging or tuning a model before deployment. In the following experiment, we use the previously mentioned 4 targets and 4 models and compare them using up to 8 different TVM schedules, which gives us the 100 data entries shown here. Let's go through it step by step, starting with the used layout for the data and the kernel. What we have here is the NHWC, or Janet's last layout, which is the default layout used in TF-Lite models. And the alternative one, which is NCHW, or Janet's first, is also considered here. For all the 3 CNNs, we can see good improvement in terms of measured inference time on all of the devices. While for the only DNN, we only have the baseline measurements here, as the concept of layouts does not exist for a DNN. Now, let's consider alternative schedules for ARM devices instead of the default TVM schedules, which have been mainly written for x86 targets. For the CNNs, these alternative schedules do not really lead to an increase in performance. While for the DNN at the bottom, the ARM schedules perform much better in several cases, as shown here. If we now add another column for each of the targets containing the metrics obtained after tuning our models using TVM's auto TVM feature, we have a lot of data to deal with. So to keep it simple, let's only look at the single CNN and the single DNN. And I also highlighted the relative improvements due to this auto tuning here. You can see that in the first and in the last row, basically no improvements can be achieved using auto tuning. While in the other cases, improvements of 5 or even much more % can be achieved. Concluding this discussion, it can be summarized that for CNNs, it is a good idea to transform your layouts to the NCHW layout and also tune the kernels. While for DNNs, you should either use untuned ARM schedules or tune the default x86 ones. As a take-home message, I would like to mention that there also exist exceptions, and the tuning itself can be very time and resource intensive, especially when doing this on microcontrollers. In our work, we have proposed and implemented the ML and MCU software with retargeting possibilities supporting a large number of front ends, frameworks, and targets. We demonstrated how to use ML and MCU effortlessly to generate complex benchmarks and discussed the observations in the end. Using ML and MCU, we were able to generate over 100 benchmarks in under 1 hour and found out that there's currently no catch-all solution for TinyML deployment. The performance of TF-Lite Micro's framework's default kernels is miserable, indicating its reliance on optimized vendor libraries, while TVM allows to perform layout transformations as well as auto-tuning to increase the performance. We are currently working on improving the benchmarks throughput in ML on MCU even more by allowing remote execution of benchmarks, and are also looking into integrating some RTL cores as well to be able to run cycle accurate simulations. Future research can build up on this work. An example to compare ISA extensions or custom kernel libraries, such as the CMDIS-NN library for ARM targets. ML on MCU could also be integrated in existing network architecture search frameworks, or could be used for exploring the power consumption of specific devices in the future. We would be happy about any sort of contribution. And if this topic was interesting for you, feel free to try out ML and MCU by yourself. You can find all the relevant links on the slide here. And these are my used references.
Thank you very much for your interesting talk. So I'm always a big fan of machine learning on microcontrollers, and having frameworks to take up a little bit of the setup hassle is always great. So I actually have a question about these drastic performance differences in the memory layout. Do you have some ideas, some first investigation, or maybe just some guesses of why there is this really dramatic difference in performance?
You are talking about these ones and this one probably.
Yeah, between the image first and channel first.
Yes, I was looking again at it a few days ago, and wasn't able to find a definite solution, but I found out by profiling it layer by layer that the layers which perform greatly worse than expected are those with rates of a size larger than 16 kilobytes. And at least for this ESP32C3 microcontroller, I know that it has a 16 kilobyte cache in front of the flash memory. So I would guess that this is related to the memory access going through the cache to the flash. And also I verified that those extreme differences are not showing up in instruction set simulation. So it's only measurable on real hardware.
Yeah, so exciting. So it really shows how much of an influence the whole system has on the performance of an application. Are there any further questions for Philip? If not, then I have another question. Did you also include a comparison to CMSIS and N in your results? I didn't see it yet. So can you comment on that?
So I explicitly have not discussed CMSIS and N to keep the complexity of the paper and the talk low, and also the main intention of the talk was not comparing different targets or libraries. It was more to demonstrate how effectively ML and MCU can be used to do a large variety of benchmarks. And CMSIS NN, for example, is already supported by ML and MCU, and you could do those comparisons as well using the existing code which is available.
So you talked also a bit in the outlooks on power. Do you already have a gut feeling how this could be done?
No, but I think the extension mechanisms integrated in ML and MCU should allow this by adding custom targets, which also somehow interact with power measurements. But I currently have no ideas on the actual hardware setup for this.
Okay, cool. Yeah, we will stay tuned and we'll be excited on the results there.
Yes.
Yeah, sorry for dropping out there. I'm back. It was just my Zoom client strike.
Oh, good. Dennis.
So,
I filled the gap by asking a question.
okay, awesome. Yeah, so are there any further questions?
Maybe you can briefly. Am I on mute?
Yeah.
No. Hey, Philip, maybe you can briefly comment. We had earlier, I don't know if you already were in the workshop when we had a presentation on quantization and future of efficient processing. I'm wondering what's your view with all the experience that you now have developing such a compiler. How difficult will it be once the industry or people want to move towards, for example, integer 4 support for neural networks? Because there's so many stages that would have to interact with one another from the front end down to the hardware. I'm just wondering in your experience, how difficult would it be to close the gap between the front end and ultimately the hardware if we wanted to go towards below integer 8 non-standard data types?
So I'm not sure if this was a misunderstanding, but I have not developed the compilation tools here. I have only developed the benchmarking flow for the existing tools such as TVM.
Okay, understood. Still, I was wondering if maybe you, from your experience point of view, could comment on that. But I do understand if your research is slightly in a different field.
I can comment on maybe the future of sub 8-bit types in the frameworks, for example, in TVM. But as far as I know, there are not really work in this field, especially not for microcontrollers right now.
Understood. Thank you.
Okay, so we are actually at the end of your slot, Philip. So again, thank you very much for your great presentation. And now I'm pleased to announce the first break that we have in our workshop. It's been over 2.5 hours now, so thank you all for sticking with us. We will meet back at the top of the hour, 7 p.m. in European time. So it's 7 p.m. sharp in Germany. And we carry on with our CODAI workshop, with which I'm very happy so far. We are really pleased with the contributions and the audience. Our next talk will be our academic keynote from Tianqi Zhen. He was an assistant professor at the Carnegie Mellon University at the Departments of Machine Learning and Computer Science. He helps to run the Catalyst group, and he's also the chief technologist of OctoML. He received his PhD from the Paul G. Allen School of Computer Science and Engineering at the University of Washington. His master's and bachelor's degree are from the Shanghai Jiao Tong University, and his research interests include machine learning and systems, and the intersections and the advancements where these two meet. He also is a firm believer in open source and open science, which is why he published many of his research projects in an open source fashion, including Apache TVM, XGBoost, and Apache MXNet. And without further ado, please take us through your talk.
Thank you for the introduction. So can everybody hear me?
Yeah, we can hear you.
Yeah, so thanks everyone for coming to the talk. Today I'm going to talk about abstraction for machine learning compilation. So to give a motivation for this audience, hopefully, I don't need to give much of motivation, but one of the things we notice is that the software landscape is changing as we are moving towards an AI age. Right? Traditionally, if you look at what defines the software, you can find that a lot of them look like a funnel. So you want to cover a broad range of applications that run a smaller set of software libraries that finally most of them you need to run on general purpose processors, such on my laptop or on another computer. But as we move to the age of AI, you can find that the software landscape start to change in terms of both what kind of application you want to target. The application start to become high-level machine learning models such as residual net, LSTMs, and transformers. The data that you are going to, additionally, you want to be able to feed in a big data set to train those models. And finally, the kind of hardware backend you're looking at start to change very rapidly, right? Not only you want to be able to target general purpose processors, but now the computing environment starts to mean, GPUs, your embedded devices, mobile phones, sometimes, distributed clustering. So there's a huge question on how can we continue to be developing our software in a sustainable fashion and effective fashion in the age of AI software evolution. And as a result, machine learning system become a key themes in a lot of the domains. And there's always a question about how can we build effective machine learning system that deploy machine learning models onto a wide range of environments, such as CPUs, GPUs, accelerators. And the approach so far had been involves a lot of specialization, right? Ideas that for each of kind of hardware backend, like CPU, GPU, there will be a special team whose task is just to go and optimize lower level libraries for those specialized hardware backend. And it's very labor intensive task. And up until now, maybe perhaps only NVIDIA is barely successful in being able to catch up with the demand. And as a result, there's a huge question about, not only how do you build in novel hardware for machine learning accelerations, but also how do you keep up with the software stack for all those evolutions. And that's where ML compilation as a new field comes in. So the high-level machine learning compilation is trying to build this machine learning compiler that allows us to be able to take high-level models and be able to do direct code generations that take in the models and generate code that runs on the environment of interest. This is an emerging field in the past 5 years, and there have been a lot of progress along this direction. And the key idea here is, can we enable a bit more automation, right? So today I'm going to touch on two big questions that we have been asking on ML compilation. The first question that we want to ask, how do we effectively represent effective machine learning programs? Of course, this representation need to be able to also capture the hardware environments that help us to do optimization on the particular hardware targets. And the second question is, how can we effectively enable automations, which, like auto-tuning, automatic scheduling, but still leverages domain expert input, because we know that, we know a lot about those hardwares, and there are a lot of HPC experts and other experts who would otherwise be able to, span their knowledge and also come and, bring in better optimized programs for. So these are like two questions that we want to ask in ML compilation. Today's talk, I'm going to focus on two pieces of work that we have been working on over the past actually 2 years on those two problems. So the first question that I want to ask and the first work is called Abstraction for Tensorized Program, and this is going to be a paper that's going to appear in S+ in the incoming year. And the paper's title is TensorIR and Abstraction for Automatic Tensorized Program Optimization. So the problem I want to try to solve in here is that if you look at the training hardware, Originally, when we started building computers, we try to have this fine-grained instruction that allows us to be able to specify how do we compute each element of the target data. And as we start to work on modern processors, a lot of modern processors come with SIMD, right? So that comes with vector instructions, but those SIMD instructions are also harder to program because you kind of need to leverage intrinsics to be able to target those cases. And finally, we are moving towards a world where we have more tensorized computing. So that means that we have hardware that contains, matrix instructions, multi-dimensional loads. All those instructions start to target, multiple dimension tensors in some form. And however, our programming is still we still leverages the traditional programming model that was originally designed for scalar computing, somewhat adapted for vector computing, but certainly not necessarily adapted for the tensorized computing. So if you look at a particular program that you might write in those modern tensorized processing unit, you'll find that it contains several elements of those programs. So first of all, it will contain some kind of loop nest that allows you to iterate over some of outer loop. There will be multiple dimensional data load, or in certain cases DMA, that allows you to load different kind of data onto specialized tower storage. There might be opaque compute operations like matrix multiplication operation that takes data from those specialized tower storage and perform certain kind of accelerated instructions. And finally, there will be multi-dimensional data store that stores the data back onto some form of DRAM. So this is kind of a typical example. It's of course pseudocode that illustrates what kind of operations that a tensorized program can perform. So now let's take a look at what are the existing approaches to represent those kind of programs. One of the approaches we call bottom-up approach, and that has been an approach that TVM took so far. The idea is that I want to be able to represent those programs through a set of loops nest and a scalar body, where the body of the operations is, it specifies how do you compute one scalar element of the target. And then we'll be able to do loop transformations along the outside loop nest. So that we'll be able to transform the loop nest into other forms, while the scalar bodies also get transformed along the way. That has been approached in cases such as halide, MRFI, and TVM's tensor expression scheduling. The problem is that in this approach, it's harder to represent tensorized compute body because each of the body here is effectively a scalar loop. Another approach that has been taken by other abstractions such as Phi-n from NVIDIA and Stripe is that you try to do a recursive decomposition of a task into smaller ones. So you start with a matrix multiplication of NMK, you try to decompose it onto 128 by 128 matrix multiplication, and then you'll go further and decompose it into a smaller form. The advantage of this top-down decomposition is, of course, it's you could take an intermediate stage and say map that onto a tensorized computation. But on the other hand, in certain cases, we still want to be able to perform loop nest transformations, which is not presenting in this top-down fashion. So the key idea of TensorIR is that can we take insights from both bottom-up and top-down approaches, right? And trying to provide what we call divide and conquer, or divide and solve approach. So the idea is we will introduce a key abstraction called block that allows us to be able to divide the loop nesting into outer and inner loop nest, where each of a block help to isolate the outside computation from the inside. After we have the block, we'll be able to continue to transform the outside loop nest by looking at some kind of sufficient signature on the block, so that we will be able to continually transform the outside loop, except that your body is now a tensorized body. We'll also be able to independently map some of the intermediate, internal block bodies onto the acceleration instruction provided by the backend. For example, we could map 4x4 region onto accelerated 4x4 matrix multiplication, or in other cases, if the acceleration instruction is not available, we can go ahead and continue map them to the vanilla for loop in here. So the key idea is that we want to be able to divide the problem into a sub-tensor computational block. And second thing is we also want to generalize loop nest optimization. Originally, when you do loop transformations, your body is always a scalar. It's a scalar computation. So you might want to track the dependencies of what is the scalar depending on another one. But now your body becomes a tensorized computing region. So you want to be able to track the dependencies along regions of tensorized computations. And then finally, we want to be able to have a combination of these two approaches. You can divide and you can generalize loop optimization. So you can do them in arbitrary order, depending on what kind of optimization you have in mind. And we try to work on TensorIR in what we call Pythonic form called TVM script that allows us to represent the overall computations using Python AST dialect. And it contains the common suspect that you might encounter in different programming models, right? So we have like multiple dimensional buffer that allows us to represent multi-dimensional access, a loop nest, and finally computing blocks that correspond to either a scalar computation or tensorized computation. And of course, because we introduced the block itself doesn't necessarily have to correspond to a scalar computation, right? So in this case, this particular block represents a vectorized computation of 8 elements at a time. And you can notice that there are read and write dependencies being marked at the block side so that when we're doing loop transformations, we'll be able to use those information for analyzing and write the programs themselves. In some sense, we're trying to introduce this tensorized computation as a first-class citizen. And one of the key idea and key design element in a block is what we call block signature. So for a given block, there is, of course, internal block computation body, and there are outside loops, right? What we want to do is we want to try to independently isolate the block body from the outside. For example, in this case, my block body could become something else, right? Could, not implementing a block body using a loop, but I can directly use the accelerated tensor instruction to implement this block body. And those dependency information are getting tracked in the block signature. So for a given block, we will have, for example, read-write regions of a block telling that, for each step in the block, how many, what are the regions of input and output that this block is touching at, as well as their read-write dependencies. Additionally, we'll also specify the iterators that block can take. For example, in this case, this declaration says that, in this block is expecting 3 iterators, Vx, Vy, and Vk, and both Vx, Y should be data parallel of length 16, and Vk should be a reduction axis of length 16. So in this case, if you're trying to bind a long loop nest, for example, if I try to make case extend to be 17, then there will be an error in this TensorIR. So in some sense, the block is declaring what kind of iteration is expecting, and then outside loop nest is trying to satisfy that requirement. So the advantage of having those block signature information is that it effectively isolate the internal computations from external loops. So as we start to do loop transformations, we don't have to look at the body of the block, but the block signature is sufficient for us to be able to deduce what kind of loop nest transformation we want to do. And once we have the block, the block is kind of like a basic unit of scheduling. In this case, we could have, each of the root function will have a root block, and we could have several loop nests whose leaf is another block. So a block is schedulable if it only contains a loop nest and a sub block as its leaf. For example, in this case, this loop block is schedulable, which means that we will be able to rewrite the loops around them. But this internal block is not schedulable because it contains, my fancy vector add one, and that's an opaque operation that we cannot analyze. So for schedulable block, we'll be able to go ahead and perform transformations on them. For example, in this case, I could say that, for a given loop nest, I can say, get block producer A that gives me the producer A's block in this case, and then I'm going to get loop K. Finally, I'm going to say that I'm going to compute the producer A at the K's location. After I do this, what's going to happen is that the schedule is going to take this IR, and you're trying to analyze the block signature of block B using those dependencies, and then deduce, what kind of transformation we can do. And in this case, it's going to move this loop nest onto this internal path and updating the corresponding production region that satisfies the producer-consumer dependency. So if you compare it to a traditional scheduling language like TVM's tensor expression language or Halide, you'll find that it's quite different in a sense that we're trying to introduce what we call interactive scheduling. So instead of trying to do all the scheduling at once and generate code, every time in each of the step when we're doing things like compute add and the get loops, they are interactive. So every step is actually really transforming this IR from one to another. It's also more modularized in a sense that our analysis is only depending on block signature, and there's no scheduling tree for us to consider when extending new schedule primitives. So it's really easy for us in this case to extend new transformations, because all you need to consider is how do you take a stable tensor IR and perform transformation. Of course, depending on analysis, give me another transformation of tensor IR. And in this case, it will allow us to generalize to more imperative schedule primitives that allows us to explore a broader set of search space. Of course, another thing that we can do is we can try to take a loop nest from the block, outside the block, and try to call blockrise. In this case, it allows us to create an independent block that encapsulate that loop nest. So this is very helpful for us to be able to take a tensorized computer region and mark that in isolation for us to do further transformations. And that's where the tensorization comes in. So the idea is we will be able to take the original workload that's kind of like a plain loop nest, perform transformations, and then substitute and do blockization, then substitute the internal block with the equivalent tensorized computation. As part of tensor IR, we also started introducing what we call automatic tensorization. The idea is that we'll be able to take the input that is written in plain loop nest of scalar body, and the tensor intrinsic declarations that describes what is the semantics of the corresponding tensor instructions, as well as the implementation that describes how I can map the corresponding computations onto a lower level accelerating instruction. For example, in this case, let's assume that it's an efficient dot inner product instruction that we can leverage in here. Once we have the tensor intrinsic declaration and input, our algorithm is going to generate candidates of possible tensorized program match that transforms the original program onto a block that can be mapped onto this, that can be matched to the declaration. And then after that, we're going to generate outside program to loop net transformations that contains things like different caching decisions and different loop nesting decisions. And finally, we're going to do evolutionary search over all those possible solutions to find a good program. And in order to see what kind of improvement we can get, here's the example of running this tensor IR comparisons compared against traditional TVM as well as tensor RT, which is NVIDIA's in-house vendor-specific library. You can find that first of all we can get competitive performance on certain cases from ResNet. We're about maybe 80% to 90% slower, but it's kind of amazing on how automated solution can already get to even close to those vendor-specific solutions. And you can find that one of the important things is we will be able to automatically support emerging models. In certain cases, for example, in here, this vision transformer was not readily supported by tensor RT, but with tensor IR, we'll be able to quickly enable it and get us better performance than the existing baselines. Another thing is that we'll be able to take the same algorithm and apply it to two different power backends. For example, in here, we apply it to ARM AWS graphics in 2 instances. You can find that tensor gives better performance than existing solutions such as TVM and PyTorch. Okay, so that's the first part of how can we go and build better abstractions for optimizing tensorized program. So in the second part, I'm going to talk a bit more about how we can do automated program optimization. And this is going to be a paper that's going to appear in the incoming Europes. And the paper's title is called Tensor Program Optimization with Probabilistic Programs. And you will be able to find the preprint online as well. Okay. So in order to do automatic program search, one of the common approach we take is for a given operator, we try to turn that on to some kind of specification like a vanilla loop nest. Then we try to generate a search space of possible program optimizations. that contains different kind of lower level program variants. So in certain cases, it might map onto the lower level, they might map into lower level hardware intrinsics. In other cases, you might want to do things like loop tilings, or in certain cases, just map into vanilla loop nest program as well. So most of the framework for automation will try to give you an initial program, specify some kind of search space, and then try out different kind of configurations, do benchmarks on the target hardware, and use those target hardware benchmarks to learn statistical cost model, then guide the search. And a lot of the questions that previous work have tried to address is, how can we build an efficient search algorithm, the cost models for a given search space? But one of the key questions that we really want to also answer here is, how can we effectively define and construct a search space? Because in a lot of cases, if you start to encounter new models, new hardware, the search space itself is the most tricky part. So, and in order to do that, let's come back to the question about how can we parameterize a search space, or how can I parameterize specifically a single instance of tensor program? This might seem to be obvious, but if you start to think about how can I parameterize a tensor program, of course, one of the key parameterizations, let me define search space by the original abstraction, right? So I will be able to say, I'm going to define my search space for all the program that includes things like parallel, for load and store and so on. So you can find that on the right-hand side, these are the direct IR representations of the program. And indeed, this is kind of one valid way of write out the program. If I'm going to write out the program, normally you're going to write out directly the code itself, right? However, to the computer, there's another interesting way to represent a program. The idea is that you start with the initial program, E0, and then you try to append a list of transformations onto this original program. For example, I can say, let's do split I by 3284. And after these transformations, you can find that the original program plus the first step transformation, it still gives you this program on the right-hand side. That's kind of like a E1, right? So E1 is equivalent to E0 plus step 1 of transformation. If you go ahead and do it further, to parallelize and vectorize, you can find that you'll get E star on the right-hand side that correspond to E0 plus 1, 2, and 3 steps. So the key idea here is that, for a computer, you don't have to represent your programs as this original loop nest. You can represent it as an original program plus a sequence of transformations. So why is that useful? Because the sequence transformations is kind of a sequence, right? It's much easier to model than in arbitrary programs. Then what we can do is we can try to construct search space through a sequence transformations. Of course, if you still use original scheduling transformations, all those transformations are deterministic. As a result, you're only going to get one program. We're interested in getting as many programs as possible, right? So in order to do that, actually, there's one extra idea that we try to do in here. So this is called stochasticity or stochastic transformation. So the idea is that we are going to introduce randomness onto this transformation by introducing some primitives such as sample tile, a sampling instruction that allows you to sample a random variable. For example, in here, we are going to sample the tile size and compute location in here. And those follow-up transformations is going to depend on those sampled random variables. So for example, on the right-hand side, if my sample of sigma ReLU on the left-hand side is going to be J1, then it's going to give me the final program on the top. But if this sampled sigma ReLU is J0, it's going to give me this another program on the bottom, on the right-hand bottom, right? So you can find that depending on how I'm going to roll out this particular program, I'm going to get different variants of programs throughout this sampling process. And one of the interesting things, if you have heard about the term probabilistic program before, you can find that effectively we are defining a domain-specific probabilistic language for transforming the programs. So once we have this probabilistic programming, actually it is very powerful. That allows us to construct a modular search space. For example, I could have a transformation module called multi-level tiling. The first go and analyze, what kind of a current program looks like. For example, I can say the current program contains spatial and reduction loop. After analysis, it will then try to go ahead and decide on what kind of transformation you want to do. For example, if it is element wise, maybe we don't need to do tiling, and we try to go ahead and do inlining. But if it's more like a matrix multiplication or tensor construction like operations, let me go to try out multiple level tiling by sampling the tiles and run split along the way. So the key idea here is we can go and combine domain-specific program analysis with probabilistic program transformation. And you might notice that in each of those probabilistic transformations actually is a programming sketch rule in automatic scheduling that allows you to be able to look at the current program and decide on what kind of optimization you can do in a very generic way. So this is an approach called meta schedule. And one of the interesting things of meta schedule is it generalizes and unifies all the previous approaches of automation and the program transformation. For example, if we are going to not supply the randomness into the process, where I'm not going to do random sampling, I'm going to manually specify all the sigmas, all the random choices in there, then becomes a manual transformation or manual scheduling that we had in before. If I'm going to go ahead and declare all the possible random variables in the very beginning of a program, looks very like auto TVM style template that where you declare all the knobs, and then you, depending on the knobs, you're going to write a template on how we are going to go ahead and transform your program. If you're going to do analysis-based transformations like the multi-level tiling modules that we had in before, you can find that the generalized automatic scheduling sketch rule generation. So effectively, meta schedule in one program paradigm through probabilistic program transformation, it covers all the previous approaches we have so far in a single API. And of course, in order to be able to effectively evaluate the possible program space, one way is we can of course go ahead and roll out this multi-level tiles multiple times. As each of the time the sample tile is going to give us different inputs, and that allows us to have like a randomized samplings of all the program transformation we have. We had a bit smarter approach than that one. So the idea is that we're going to try to roll it out, but also trace the key operations, including the sample and transformation operations we have. Where each of a trace, the cell still contains those random numbers in here, right? So for a trace, we'll be able to mutate, for example, the decisions of all the sigmas in here. And as a result, for a given trace, we can continually run evolutionary search for the rollout trace of those original probabilistic programs. And as a result, doing like mutations on a trace and evolution on a trace is more efficient, as a matter of fact, because these mutation evolution doesn't have to happen on a front language like Python. We can have a specific trace mutation and evolutionary rule that help us to continue go and optimize the possible choices. So the high-level overview of the overflow is like this. You will take initial programs, you transform, you have a collection transformation module that gives you a set of traces, and then you're going to do evolutionary search guided by a cost model to find a good probabilistic decisions of those traced programs. And finally, we will select a good program among all the specific instance of traces we have. One of the interesting things that we talk about, so far we talk about meta schedule and TensorIR, right? One of the things that I do want to mention is that they are designed to fit together. So in this case, TensorIR supports the program representation and transformations, and meta schedule handles the search space generation and automatic scheduling. So there are also modular ways for us to extend the search space in certain ways. For example, if you want to add things like tensor call handling, likely you only have to add meta schedule sketch rules, and you can even add that through Python if necessary. So here's an example on how we can use meta schedule to quickly enable different kind of sketch rules. And you can see that as we add more sketch rules, the search space can become larger, and as a result, we can get better performance along the way. And finally, we have heard talk about relax, right? So one of the key goal in here, and one of the key lessons we learned in the past few years, is that not only want to build all those components, we want to have those components to organically work together with each other. So TVM unity is the main theme that the TVM community have been collecting and pushing for this year, with the goal of trying to unify in all the perspectives. You have already heard about TensorIR and how it's going to interact with meta schedule component that allows us to do holistic program optimization and tensorized program optimization. In Andrew's talk earlier today, right, you heard about relax. And additionally to that, we also have a TVM FFI that allows us to incorporate arbitrary library functions from the environment onto this overall program. So our goal is trying to unify all those aspects and have all those program instructions sitting in a single Pythonic IR module that is shown on the right-hand side. Right? So in this case, you can find it contains all the elements, including tensor IR, tensor level computations, library calls, as well as relax function that allows us to support symbolic shape and direct invocations onto the tensor IR programs. We believe that by unifying everything together, actually we can bring in additional optimization capabilities and also provide a common ground for us to further build more exciting machine learning compilation ideas. So that's the two works. So I do want to come back and mention Apache TVM is open source community governed by top level Apache governance model. We have a growing number of developers every day. And there's an annual conference, TVMCon, that get participates from major industrial players. So there's a call for paper of TVMCon that's out today. And the deadline I think is quite is in a few weeks. So you are more than welcome to submit your proposals to there if you are interested in working together on and present your work about related machine learning compilation and acceleration. Finally, machine learning compilation is an exciting new field. A lot of things are yet to be defined and a lot of things are yet to be explored, but it also starts to have important applications in both industry and academia. So one of the efforts we have been studying recently is also trying to create a set of educational materials around machine learning compilation. Of course, it's an evolving thing, and we had a first iteration of the online class called MLC Machine Learning Compilation in the past summer. We are going to offer more materials as part of this effort as well. If you are interested, you are more than welcome to check out mlc.ai for more details. Okay. With that, I would like to conclude my talk, and I will be more than happy to take any questions. Thank you.
Thank you very much for your talk. It was really interesting, and also thank you very much for pointing out additional educational resources for our guests. So I think that is highly appreciated by all of them. So, and with that, I would like to open the floor for questions. Please go ahead. Okay, so if I have to break the ice, then I'll do it, of course.
I have one, Dennis.
Oh, okay. Okay, go ahead, please.
I mean, there are so many cool new features like Tensor IR, Metascheduler, Relax. So do you think Relay, TE, and auto-tuning will eventually remain as also as features, or are they going to be replaced?
That's a great question, Michael. So as of now, right, we certainly want to make sure that, because TVM is a large community, we want to make sure that some of the existing solutions remain stable for the users, right? So as a result, for example, TE and Relay is still going to continue functioning for a while. On the other hand, you'll find that, for example, Metaschedule already encapsulates the capabilities that auto TVM and auto scheduler have. So it's very natural, right, for us to be able to, and additionally, it's a reduced set of APIs. Originally, if you learn auto TVM, you need to learn another set of API other than the scheduling API. Right? So we do expect that the community to continue to move towards Metaschedule. Same for the TVM Unity. So the idea is that we want to be able to, for us to move to this world where not only we have all those awesome features, but have them work together with each other. And that's where kind of next level of quantum leap can come in, because having all those things work together means that we no longer have to do hacks for certain things like Relay plus auto scheduling. And that's going to enable us to have more explorations for the future. Yeah.
Cool, thanks.
Great. Maybe also referencing the talk we had before the break on ML on MCU. So what you talked about was now very, let's say, removed from the actual use case and the hardware. You were really talking about infrastructure topics. So where do you see the challenges in the tiny ML and in the embedded ML area, where often these tuning opportunities aren't so big because the hardware isn't so complex. So do you think there is a different set of things that needs to be done in TVM to have a better support for these kinds of devices?
That is an excellent question. And that's where kind of TVM Unity try to come in, right? Originally, TVM, I think, was designed in a very tuning heavy infrastructure, right? So we kind of like we expect, you kind of have to come in and do auto tuning for everything. But as we start to move towards TVM Unity, tuning start to become just a transformation path. So the idea is, if you want, you can still go ahead, take your operators and apply tunings, right? And then use tuning. If you have a tuning logs, you can go ahead and apply them. But we also allow you to directly present, for example, if you have a more specific set of ideas of exactly how I'm going to leverage my data transformation and so on, right? You will be able to use, say, meta schedule APIs to do a set of manual version of space that is smaller, and maybe it's not like maybe you only need to try a few choices, right, to be able to narrow it down. So indeed, I believe that in different problem space like TinyML, like server class accelerations, there might be different solutions for machine learning compilation. And one of the key questions that we always ask today is, how can we enable all those explorations to go ahead, right, while working on a common foundation, so that you don't have to rebuild your importers, you don't have to rebuild everything from scratch, and even you can do that exploration through Python, and so that you could quickly hack it up, try it out, and see what's going on. So that's what TVM Unity try to offer, and indeed, it will allow us to do things like, instead of doing auto tuning, maybe have a way to map to accelerator libraries when possible, and have a set of heuristics that we can, go ahead and schedule some of the default operators like element-wise and reduction. Yeah.
Okay, maybe then following up on that, actually, you said something good. So having accelerator libraries or maybe doing auto tuning. So are there plans to also provide features to do, let's say, system level optimization of a network? So for example, you have a microcontroller plus an accelerator like ARM's NPU engines.
That's right.
And then have a process that gives me the best split of when to work on the controller and when to work on the NPU.
That's a very important point, right? Again, I believe what we are trying to talk about here provides a foundation to doing that kind of explorations. We had another paper called Collage that tries to effectively, try out different combinations of dispatching overloadings and try to pick among best of them. I believe, and you can find that in order to do that, you can imagine what the action will look like. It's not going to look like a traditional compiler, because traditional compiler is kind of a pipeline. Right? You take something, you do transformations, you get something out. But now you kind of need to write something like 4 different choices of partition, right? Do lowering, run benchmarking, and then come back and select, right? So then, of course, you can go ahead and bake that into compilation pipeline. But on the other hand, one of the things we want to enable here is, can you go ahead and just write that in Python, and having those mechanisms while you have those transformation mechanisms and other things, right? And so that you can quickly try out different ideas of partitioning, offloading. And once you are certain, hey, here's a possible approach, you then bake that into your compilation pipeline in a much more efficient fashion. Yeah.
Okay, so fascinating. So you want to break up this traditional notion of the compiler a little bit to make it more
exactly
tool for experts.
Yeah, to make it more like because if you look at deep learning land, originally in the first generation of deep learning, Caffe is a bit like compiler. Right? You take a protobuf, everything is a black box. It's really hard to explore. But then in PyTorch, you will be able to customize your models and all the other things in Python. Right? Similarly, I believe it is a time for us to, when you look at machine learning compilations, also do that through IPython notebook, being able to customize as much as possible, write for loops if necessary, right? Have all those tools that allow us to do this exploration, and that's going to help us to get to our goals faster. Yeah.
Yeah, that's really awesome. Yeah. Now I talked enough, so I guess there's also other questions from the audience. So please go ahead.
Yes, I have another question, Miguel here. I was wondering, from a more practical perspective, one feature that I explored a little bit in the past, what is called BYOC, or Bring Your Own Code Generator. So I'm wondering, how this fits into these new features. The reason I'm asking this is because, if you have out of the box support in your backend from TVM, then it's great. Everything works nice. But sometimes you have a particular target hardware where TVM doesn't have a backend for that, so you need to use some sort of API library, and then you still can profit from TVM while interfacing with your custom API. So I was wondering, how this comes together.
That is a great point, right? And indeed, BYOC is a very important feature in TVM. And as a matter of fact, the design of Unity takes that in mind in a first-class citizen. Specifically, if you look at these 4 quadrants, right? There's a quadrant called TVM FFI. TVM FFI means that effectively, how can we effectively call into external library APIs through what we call pack function mechanism. So I'm in here on the code on the right-hand side, there's a call pack to customize in place update that could be defined by an external accelerator library or any other cases. Previously, in the original TVM land, BYOC is kind of a specific feature that baked onto a particular kind of compilation pipeline. So it's a bit hard to customize BYOCs in some sense. But now in this TVM Unity land, actually BYOC will also become a normal compilation path. So the idea is that we're going to detect a possible subgraphs. For example, in this case, I might detect there's a dot and flatten operations that my accelerator can take. I'm going to just write that onto a call packed onto my accelerator library. So effectively, it's become more modularized. And you can even combine BYOCs with other optimizations, like I can do BYOC for part of my computation. Then I'm going to leverage automatic code generations for the rest. So that is kind of like a more powerful combination that you can get under this new paradigm. Yeah.
Okay, it's great to know that BYOC is considered as a first-class citizen in this new set of features. But do you see any, let's say, obvious or concrete limitations when you use this type of libraries? Because I guess, depending on the library that you have, maybe you can express things in one way or another. But is there any potential limitation there?
I would say, in terms of like a BYOC, right? So we are going to support most of BYOCs that originally supported through BYOC. But of course, if you are going to have more opportunities like Fusion and other cases, right? So having some form of native support is still going to be helpful. But again, our goal here is not trying to be opinionated. We want to be able to provide a foundation so that we can try out, right? You can go ahead and try out, hey, this part, let's try to offload to BYOC libraries. This other part, let's try to do automatic scheduling and being able to mix them together, so that you don't have to solve all the problems through a single approach.
Okay, thank you. Sounds good.
Are there any further comments or questions to Tian? If not, maybe I have another question. So currently it's at least my state of knowledge, which could be a little bit also exploring different memory layouts or tensor layouts wasn't really possible in auto tuning in TVM. And as we saw earlier, this can have quite a big effect on the performance of a program. So is this also something that's coming to Tensor IR?
That is an excellent question, and indeed it is something that on top of our mind. For example, actually, from an auto scheduler land, there's already some consideration. So when we are going to reorder the loop orders, one of the things you can do is you can reorder your memory layout weight as well, according to the loop orders of the program. And that have a significant impact. As a matter of fact, the reason why auto scheduler is faster in a lot of cases than auto TVM was because there's an reordering of the memory from a weight. Right, so indeed, Tensor IR comes with some memory reordering instruction as well. However, in order to do memory ordering, you also need to propagate that memory ordering to your inputs, right? So that's where relax comes in. Like originally, it's really hard to express because when you are transforming a Tensor IR function, your interface needs to remain stable, right? You still, when my Tensor IR function expects certain layouts, if you want to transform your input layout, you have to transform all your consumer, all the producers of that as well, right? So originally it's really hard to do that kind of transformations. With Relax, actually, it's become much easier. So what we can do is we can go ahead and transform the tensor IR, and then try to split out some of the layout transformations onto the Relax graph level, so that you will be able to have a call onto a packed version and some pre-packing operations in the graph. And then those pre-packing operations can either get canceled out or get constant folded if they are weights. So indeed, this is a very important consideration and something that we take very seriously. And that's one of the motivation actually for us to be able to co-design those things together, because it's really hard to handle that in a single layer. Yeah.
Okay, fascinating. Okay, are there any further questions? If not,
so is there
then
any thoughts on? Sorry.
Yeah, go ahead,
are
please,
there any thoughts? Are there any thoughts on altering the definition of the target? So, for example, mapping different parts of a tensor IR expression to different parts of hardware. So, like you have multiple processors, multiple accelerators. So you could, for example, in your part here, that you could map certain blocks to certain subgroups of the hardware.
That's an excellent point. So up until now, we have not concretely tried that, but I would imagine that tensor IR abstraction is already readily designed for that purpose, right? For example, you can, because effectively, what it amounts to is you kind of need to introduce, specific memory regions as well as mapping each of the blocks onto different parts and being able to track the dependencies among them, right? So if there's a concrete hardware in mind, I would imagine that this block data structure actually help us to be able to do that kind of mapping. Yeah.
Oh, thanks.
Okay, then let's move on. Thank you again very much for your talk and taking time to discuss your work and your research with us.
So this brings us to the next point in our agenda. It is a talk on embedded AI challenges in perception systems by Miguel, who is here on the talk, here in the call. I heard you just also having a discussion. To briefly introduce Miguel, Miguel is here from Aptiv. He holds a doctoral degree in electrical engineering from RWTH Aachen University in Germany, and a master degree in embedded systems design from ETH Zurich, University of Lugano, and Politecnico di Milano. His main research areas are embedded system design, embedded AI, compiler technologies, software optimization, and parallel and heterogeneous computing, among others. So a perfect fit to this workshop. Multiple of his research results, including his doctoral work, have been successfully transferred to the industry, and he both published multiple academic publications and filed multiple industrial patent applications. He's currently working as a senior expert for embedded AI at Aptiv, where his main activities revolve around efficient, accurate, and cost-effective deployment of AI algorithms. So with this introduction, I would like to hand over to you, Miguel, to present your part.
Thanks, Sebastian, for the introduction, and also to you and Michael for the invitation to this nice workshop. It's a pleasure to me to contribute to the discussion on Edge and embedded AI. And my topic today has to do with the challenges, particularly, in terms of embedded AI, but particularly in the area of perception systems, which is what I'm working on right now at Aptiv, aiming the domain of automotive applications. So let's get started. So one of the key drivers, as you know, for having more and more AI applications, particularly also in the automotive domain, is the advances in AI accelerators. Actually, there are many players and many ways in which the AI accelerators have been evolving. And this, of course, enables to deploy more and more complex algorithms. And the perception systems are not an exception. Actually, in terms of vision, is one of the areas that has been a pioneer both in the academia and industry. And many AI vision applications or solutions are already state-of-the-art, and they outperform classical solutions. But obviously for automotive, and as you may know, we have other sensors which we can use in order to achieve sensor fusion. And we can mention, for example, radar, LiDAR, ultrasonic, which are also following. But this also opens a new dimension of challenges, because many, or if not the great majority of solutions today in terms of embedded AI are tailored or highly, driven by vision. But these new sensors open new challenges in terms not only about the data or the nature of the data that they provide, but also in terms of the algorithms that are associated to these sensors. And this is one challenge, because when we are trying to deploy algorithms for those sensors, we see sometimes there are gaps, right? That's one aspect, because solutions have been highly focused on vision. The other aspect is, of course, there is missing tooling and standardization, given that there are many actors in many domains associated to embedded AI. So the way I like to present today the challenges that we have seen in practice, in real world, let's say, while trying to deploy algorithms from concept to reality and hopefully a product, is based on the idea that we start with a perception algorithm development, where we have a team which basically is developing the algorithms in any of the AI ML frameworks that you know. And then we follow several steps as presented here, starting from embedded aware training, which basically means that we are already considering the target architecture from the training perspective, which was not the case at early stages. Because now, we will talk about QAT, hardware awareness and other things that, you are already bringing the hardware awareness early to the training flow. Then we have also graph surgery, which tries to make the graph a bit more embedded friendly ahead of graph compilation. And then graph compilation, of course, there are multiple challenges, many of which are addressed and by TVN, which is a great example of this domain. We also have multiple challenges in terms of target optimization when you start implementing things by hand and handwritten code. Then you move on to the KPI evaluation, where you want to see if your target performance and accuracy are met, especially for, let's say, requirements of your customers, especially which are very strict in automotive domain. And one aspect also in the KPI evaluation is to understand how much resources your hardware needs or your algorithm needs, because this is quite important for the next step when you integrate multiple algorithms together and you have a limited budget. So, and this is one aspect which is typically not considered, but it's a real world problem that you need to, let's say, make sure your algorithm, is within the resource constraints that are offered to you. And with that, you can hopefully iterate, or when you're happy, you will end up with an embedded AI product which could address or consider multiple sensors. So let's get started a little bit with the training part. I think in the first keynote, QAT was briefly mentioned, and this is nice because it's aligned with the first keynote. And here there are multiple challenges that we see. One thing is in terms of training configuration when you go with QAT. So you have to decide what type of strategy you follow. Do you collect the statistics to understand the min and max values for defining your scales? Do you learn quantization parameters? Another question is when you activate your fake quantization nodes, which are the nodes that basically model quantization during training. Are we starting right from the beginning, in the middle of the training, after a few epochs, or towards the end? And then there is another challenge, the hardware awareness of QAT, which in my opinion is one of the key challenges to apply QAT in real life. And that is, you want to model quantization during training to make sure your accuracy is good, but you have to take into account what is the characteristics of your hardware. And that means, how my target compiler is doing fusion of operators, because based on that, I know where to place fake quantization nodes correctly. Then we have multiple, let's say, strategies for quantization? Are we doing channel-wise or layer-wise scale quantization? Do we have symmetric or non-symmetric quantization? Do we have uniform, non-uniform? Do we use power of two scales or we use linear scales? So we have a lot of characteristics, and we have to understand our target architecture to properly model this in the QAT stage. And for all of that, yeah, one last challenge is the missing standardization. Because every hardware might need a specific library based on what I just mentioned before, the hardware awareness. And when you're dealing with multiple suppliers, they provide their own libraries, and you need to use this library in order to, let's say, apply properly QAT for that hardware. And while doing this, you might end up implementing multiple times your code for your model in PyTorch also, because then you have to use specific libraries, and this leads to lack of standardization. And that also has to do with how the QAT meta information is parsed from the training step towards the actual implementation in your target graph compiler. So those are a few of the challenges that we have seen in terms of QAT. Now, is still in the area of training. Better training, we also have pruning as an important compression technique. But here the problem is more about the choices that we have. We have multiple granularities for pruning that you know very well, I guess. Weight pruning, channel pruning, layer pruning as well, even. And the question is how to mix and match correctly these different granularities to achieve, say, the best approach or balance between accuracy and compression. So it's a significant search space. And beyond that, there are other choices that you have to make in order to apply multi-grain pruning or pruning in general, whether you do global pruning, local pruning, whether you do one-shot strategy, iterative. What is your importance criteria to decide what is important in your model and what is not important? And it's a significant design space exploration when it comes to pruning. And this is also a challenge that we have been facing, so to try to make the best choices here. And once you are kind of happy with the training stage, then you get a graph which is exported, and this graph typically is going to the front end of your graph compiler or your target framework. And typically, if you are lucky, your graph is going to be consumed correctly in your graph compiler. But sometimes you have a lot of problems, and this we see it, as I mentioned, we are talking about sensors that are more challenging to deploy. For example, well, we have unsupported operators because there are exotic operations being used, or we have complete subgraphs which are not deployable because they aren't supported. And then you somehow have to manipulate the graph to make it embedded friendly, or replace it with a single node that can be implemented with custom operators. And then this, of course, is an important challenge. And this is a process that is actually very difficult to generalize and automate. And also you have to interact a lot with your, let's say, algorithm team, because the algorithm team might try to, let's say, simplify the graph ahead of deployment. But there are definitely many complications, and there are things that you want to do during training which are not embedded friendly. So you have to make a trade-off and negotiate with your algorithm team to have the best interface. But sometimes that's not enough, and then is where the graph surgery comes into play. Then once you prepare this graph, saying an embedded friendly way, we go to the graph compiler, for example, TVM or so, could be. And then we hope that the compiler, graph compiler can deal well with scheduling, operator fusion, and also a challenge here is as well the custom operators that implement functionality that is not supported by default in your framework. Maybe you want to implement a full algorithm based on that, and because it's not supported out of the box. So you have to extend your graph compiler as well to understand this custom operator. And for the sake of a product development, I mean, you have to reduce the resources. And graph optimizations have to do a lot with the scheduling in order to try to reduce not only the execution time, but also reduce the on-chip memory usage. because the smaller the better and the cheaper, and this is where we want to go, especially when you want to integrate multiple models, and I will talk about that later. Another aspect of graph compilation is if you go with post-training quantization, also mentioned briefly in the first keynote. Here you have to deal with min-max values, which are typically outliers, and they are gonna hurt your accuracy. So you might want to check what different type of algorithms you can use in order to improve the accuracy of your model while quantizing it. One also very practical problem is if I use peak post-training quantization, I need calibration data. But what calibration data should I use? How can I find a representative data set? And this is altogether a big challenge. I mean, some people might say, if I'm doing a vision scenario, I will take some pictures in the night and in the day, and I try to cover multiple use cases to have a representative data set, but sometimes it's not enough. It's not that easy. So you have to find other alternatives to find, let's say, representative data sets. Now, when it comes to target optimization, we also have some optimization opportunities. One of them is sparsity. And sparsity was also mentioned, I guess, in the keynotes. That's why I'm happy to refer to the first keynote, because I see many intersections. And in terms of sparsity, there are actually two options that you can distinguish. Data sparsity, which is based on the nature of your perception system, of your radar. For example, LiDAR or radar, you can also expect more sparse data. That's more dynamic sparsity, and then we have more static sparsity in terms of weight that can be, let's say, increased by means of pruning, weight pruning. So we have these two sources, and the question is, can we profit from this, or is this going to be a problem for us? And the challenge here is that typically most of the hardware is not really having any, let's say, out-of-the-box support for sparsity, which can help us to actually profit from this aspect. And instead, you have to do many, let's say, optimizations which are really expensive. Maybe you end up densifying tensors or working with dense tensors, which waste a lot of computation and bandwidth, and you don't want to do that. So once again, the challenge here is about the limited hardware support for this, and also complicated data compression and manipulation strategies. In terms of target optimization, I mentioned that when you have unsupported operators and unsupported subgraphs, you might want to implement that as a custom operator in real life, and because there is no other option, and maybe you have an island in your graph which is really not supported. So you need to basically implement this custom operator. That implies that you have to do a lot of manual work, manual programming, and you have to optimize it very well for your target hardware. You need to know very well your target hardware. So for that, you need to exploit a lot of parallelism from the thread level down to the instruction level. And this, in practice, especially for product development, you cannot, let's say, waste any optimization opportunity, and you have to go ahead and optimize this by hand, which of course is very challenging and time consuming, but sometimes needed for the sake of achieving your target performance. Now, once you, let's say, are happy with your optimization, you go ahead and try to evaluate your KPIs and to see if you met all requirements in terms of accuracy, in terms of execution time, and also in terms of resource utilization, actually. In terms of runtime, maybe you have a target frame rate, which is defined by the requirements of your customer or the requirements of the application. You also have an expected accuracy that you need to achieve even after pruning, even after quantization. So you need to verify that. And this is not easy to evaluate typically. One of the KPI aspects which are very hard to evaluate is the resource utilization of your algorithm. So meaning how many operations do you need, how many gigaops or tops you require, how much memory do you need, so what is the budget? Because this is important for the sake of integration of multiple AI algorithms in a single product. And as an integrator, tier one, we need to integrate, let's say, multiple algorithms. and then you need to see, how expensive are each of them. So you need to evaluate that as a KPI aspect, right? So, and so far, we talk here about the challenges at different stages of optimizing or deploying a single model. But another aspect or reality of bringing AI products to the market is that there is not just one model or one application which is using a neural network model, but you have multiple of them, and you need to integrate them in an efficient way. And here there are multiple challenges. For example, high heterogeneous systems. So we have multiple operating systems on a single device, because maybe you have a host of the operating system, for example, Linux, and then you have a guest, which could be Android or QNX, or the other way around. And this is very typical in the automotive domain. So you need to deal with a very heterogeneous operating system environment. At the same time, you might have multiple layer runtime systems. You might have one coming from your hardware supplier, but next to that, maybe some algorithms might use TVM or might use TF-Lite, and then you have a heterogeneous AI runtime system environment. And obviously, you might also have multiple target cores or target hardware, and then all in a single system simultaneously. So you need to deal with this heterogeneity. And here it is very important. Another challenge is how to schedule the models, multiple models, right? How to make the best use of an NPU if you want to share it with different applications. So you need to think about the prioritization of the models. You need to think about preemption. So your operating system or AI runtime system should be able to preempt low priority model in favor of a higher priority. And this is important for automotive, especially ADAS applications, where it's a safety critical system, right? And for that, of course, you need to define the different use cases depending on the feature of the ADAS feature. And when you have this preemption and switching between models, you need to do it very, very fast according to some requirements from the customer, which are very, very strict, of course, for safety critical systems. And yet another problem of integration is that you have a big ecosystem of suppliers when it comes to the algorithms. So you get some algorithm from supplier A and another one from supplier B, and we internally develop a third algorithm, and you put this together. But because some of the applications, of course, you don't have control over them because they are just being provided as a binary or so. These applications might misbehave in terms of the resource utilization for AI. So you need to observe and try to monitor the behavior of the different AI applications. And this is let's say, a practical challenge. And also you have to detect and control those misbehaving models that maybe, they were supposed to use less resources and they start using more resources. And then this hits the whole chain and ecosystem of your application. Another challenge also, I guess, mentioned in the first keynote is encryption, which is typically not really well studied in the context of AI. From encryption perspective of the model, because if you get, let's say, different models or different applications from different suppliers, they might want to protect their IP, and you need to have in place a proper and effective encryption decryption strategy. And this strategy has to be quick, because in terms of restrictions or requirements, it's not just about that your model is running fast enough or switching fast enough between one or the other one, but it's also important that your model loading time is quick. And when you include encryption in the equation, your model loading time might be impacted. So that's yet another challenge in the domain of integration. Last but not least, the idea of presenting these steps give us a sense of that there are multiple challenges along the way when you start from the training down to satisfactory implementation of embedded AI. But you need to somehow put together these steps, and especially in a production environment, you want to make sure this is quick. So here the challenge is, how can we put this together in a, in the sense of a embedded MLOps sense, with the idea to, make this flow automatable, quick. But, the problem is that some steps are, could be partially manual or very slow to execute due to long execution or analysis and optimization time. And also how to make this such a workflow hardware aware and retargetable if you switch from one hardware to the next one, because maybe you have a system or algorithms that you want to migrate from one hardware to the next one, and then scale and with different products in your portfolio. So those are key challenges. And with that, I like to conclude my talk. Before that, I would like to mention that we are hiring, and we are also happy to have additional people on the team that help us to address these challenges. So if you are interested, please feel free to get in touch. And yeah, thanks for the attention. I'm happy to answer questions.
Good, thank you very much. There are questions.
Hi. Yeah, I have a question. So thank you for the talk. It was great. And from first hand, I know a lot of the problems that you talked about, but maybe an adjacent topic. So since you're in the automotive sector, what about general verification topics of code? I mean, when you have like tools that generate code for neural networks, they're usually not like automotive qualified in that sense. So maybe can you comment a little bit on that from your perspective of how this could be integrated into this ecosystem?
Sure. So definitely, I mean, the aspect of safety criticality and ISO and all of this is a topic which is relevant for automotive, and yet another challenge that could be added to this list. Typically, what we see is that existing tooling for deploying, or frameworks to deploy AI models into specific hardware, so far they have not been, let's say, automotive qualified. They don't use, for example, MISRA, or they don't follow ASIL-B standards. But we see more and more that the tooling from the suppliers are getting there with this type of requirement, and that means that it's not just about the runtime system, that has to give these guarantees for safety criticality and functional safety in general, FUSA, but also the tool, right? And the tools, they have to be compliant with that. So this is obviously a topic that, to be honest, what we see in practice, has not been covered, or is not in the maturity that you might hope. But the good news is that we see more and more the industry and the ecosystem and our suppliers in general getting there with the solutions, because this, of course, is a first citizen, let's say, requirement for deploying a model in the automotive domain. Yeah. So for example, that will be interesting eventually to discuss in the context of open source tools like TVM, but at least in proprietary solutions, we already see this being addressed.
Oh, fascinating. Thank you.
Thank you.
Miguel, great talk. I would also have a question on less related to the challenges that you have posted, but still related to the field of automotive aspects. What I'm particularly interested in from your opinion or things that you perceive when it comes to the heterogeneous distributed systems that an automotive car typically consists of, versus a very centralized architecture. Do you see there a trend? Because from my perception, I would think that the trend would go towards a centralized architecture, simply because, well, that's where you could put the compute, and then you don't have to deal with all the challenges of collecting sensor data and doing the right compute at the right node. On the other side, the automotive system is such a complex aspect, so you want to do some pre-processing at sensor, so you just deal with a very complex system. And I'm wondering, what's from your experience, where is the industry heading when it comes to this, well, two directions, whether it's very distributed heterogeneous versus centralized homogeneous?
Yeah, this is a great question, and maybe I can use this slide to discuss a bit on this one. So indeed, what I have seen is that the industry is moving towards a more centralized solution because of a cost reason, right? So you want to, let's say, reduce complexity, reduce wiring, reduce, let's say, costs associated to that, to have a lot of, SOCs scattered in your system. And then you want to, go in this direction of a centralized platform. And nevertheless, from the sensor perspective, you might also have small capabilities to do a little bit of pre-processing, as you mentioned, right? And that could, help to prepare the data ahead of reaching the central compute platform. And this is the trend that I see. So especially when we talk about integration. So here I'm implying you have a centralized compute platform where you might have more and more an increasing number of AI models, and then you have pressure really into use efficiently this resource, which is a centralized compute platform, which, to be honest, is not that weak. So we see that decentralized compute platforms are becoming really powerful. If you think about, talk about TOPS, it could be even more than a GPU. So you have a lot of power, but you cannot abuse from that, right? Because you need to give a space to more applications. But still, of course, if you have opportunities to do things in the satellites, or in a distributed way, you will do it. But in reality, the trend is more towards centralized compute platforms, and this is something that Aptiv has been trying to as well move forward with the smart vehicle architecture, which has been published and discussed before with the press and publicly, and this is also a trend that we see internally, right?
Thank you.
Thank you.
So, are there further questions from the audience? If not, then let's thank Miguel again for this great presentation and your insights from an industrial challenge side.
Thank you very much.
Then let's move over to the next paper. The next paper is called Integration of a Systolic Array-Based Hardware Accelerator into a DNN Operator Auto-Tuning Framework. Presenter will be Federico Nicola Peggia. I saw you here on the call. Let me briefly introduce you.
Yes.
So Federico is fascinated by the challenges presented by the deployment of AI algorithms on edge devices. And as such, he is currently working with efficient mapping and deployment strategies for neural networks on heterogeneous systems, using the TVM compiler as a framework to accelerate the implementation of his ideas. Federico studied electrical engineering at the National Technological University in Buenos Aires, Argentina, from 2014 until 2021. During that time, he also worked in industry to gain industrial experience, and he is currently a computer science PhD student at the Eberhard Karls University of Tübingen in Germany, under the supervision of Professor Dr. Oliver Brinkmann. Since 2021, he's also working as a researcher at the FZE Research Center for Information Technology in Karlsruhe, Germany. Thank you very much for being here today, Federico, and the stage is yours.
Thank you very much for the kind introduction. So let's get right into it. I hope you're seeing my screen.
Yes, we do.
Good. So this is more or less the structure of the presentation. I will give you an overview of the motivation for this work. Then I will talk about what exactly scheduling instructions means, although I think it will be kind of redundant for the audience that we have today. Then the main part comes where I will show you how the integration between the TVM deep learning compiler and the Gemini accelerator works, which is the main topic of this paper. Then I will finish by showing you our experiment results compared compared against the reference implementation, and discuss future extensions and probably improvements for this work. So this is more or less the motivation of the work. So nowadays there are a couple of open source SOC generators which are becoming increasingly popular, and they are highly customizable and parameterizable, and you can generate all kinds of different architectures. And because of the open source nature of them, there are highly customizable accelerators that are being developed for these SOC generators. The developers of these accelerators normally provide some basic C functions or instructions or C macros to run typical neural network workloads, for example, convolutions or fully connected layers. But here comes a problem, because there is no guarantee that these default functions that are provided will provide the best throughput across all possible SOC configurations and workloads that you can execute on that accelerator. So what would we like to have? Well, we would like to have some auto-tuning process to automate the search of the best instruction sequence, giving a specific workload and SOC combination. But first, of course, we need to find a way to generate these instructions and integrate these instructions into some kind of deep learning compiler in order to run this kind of auto-tuning process. So what does scheduling instructions mean? Well, typically these accelerators provide two kinds of instructions. First, instructions, let's say instructions or functions, let's say layer-wise, like CISC type instructions, where you send these instructions to the accelerator, and the accelerator executes an entire operation. For example, you send only one instruction that says execute this convolutional layer, and the accelerator takes care of everything. But there are also fine-grained instructions. So these instructions give the developer complete control over the behavior of the accelerator. And we could make some kind of categorization of these instructions in these three different categories. So configuration instructions, move instructions, and compute instructions. Let's see an example. For example, for a general matrix multiplication, this is a pseudocode, of course. We could represent the operation with the specific accelerator instructions as seen in the picture. For example, here we have the configuration of the accelerator. Then we have the move of data into the accelerator's internal memory. Then we have the actual computation. And finally, the output of the data again to the DRAM. So the goal of this project was to automate the generation of these instruction schedules for a systolic array based accelerator, and then compare the generated schedules against the standard ones provided by the accelerator developers in order to show that we can actually find better schedules by running this auto-tuning process. So this is more or less the idea. We will have some accelerator parameters, which are very specific for systolic array. We will talk about it in the next slide, I think. And then we have also schedule parameters for the specific operator that we are trying to auto-tune. We integrate these two kinds of information into the code generation framework, and we get some nice C function. We would like also for this code generation framework to generate two kinds of C functions. We will generate C functions that use this kind of CISC type instructions or layer-wise instructions. And we will also like to generate C functions that use only the intrinsic instructions. What are the advantages here? Well, a user could, for example, select based on the available resources, for example, the amount of memory he has for his code, if he wants to generate the layer-wise instructions, which would be only one instruction, or generate the intrinsic instructions, we will be much more instructions, but perhaps will be faster. And we can also compare, as I said in the previous slide, compare the performance of these two different functions. And of course, these schedule parameters that can be seen in the left bottom of the slide allow the generation of multiple combination of intrinsic instructions sequences so that we can automate the process of finding the best schedule parameters. So this is the Gemini accelerator for which we want to generate the instructions using TVM. We selected this accelerator because of his open source nature and because it also provides the two kinds of instructions we were talking about previously. This accelerator works in a tightly coupled manner with a Rocket Core CPU. This is a RISC-V CPU using custom instructions that are sent to the accelerator using this ROC interface that can be seen in the left. It's directly connected to the L2 cache, if there is one. And internally, it has some SRAMs to store data or results of the computation. It has a systolic array to execute the matrix multiplication. And it has a controller that parses the instructions received from the CPU and executes them. And of course, a DMA engine to move data in and out of the internal memory. The only thing you need to know about the systolic array is that it executes, so it's a square systolic array that executes dim by dim matrix multiplications. That's the only important thing about a systolic array. So what kind of the instructions are provided by these accelerators? By this accelerator, as I was saying, basically the CPU can generate instructions to configure the internals of the accelerator, move data into the accelerator internal memory and out of it, and instructions to actually execute the computation in the systolic array using data that is already available in the internal memory. It also has some CISC type instructions, which are processed by a state machine that is in the controller module of the accelerator. And this state machine generates the sequence of intrinsic instructions so that the user does not have to do it by hand. So it kind of alleviates the burden of generating the intrinsic instructions to the developer, and it does so directly in the hardware. The developers of Gemini also provide some C functions, which internally call the CISC type instructions, which makes the deployment of the neural networks a little bit easier, of course. Why? Because the intrinsic instructions, you need to manage all pointer addresses. You need to manage very carefully the sequence in which you execute them. So it can be a very heavy burden for very complex operators. So this is how our workflow works for the TVM and Gemini integration. We start with a model that is exported from TensorFlow Lite. This is a pre-quantized model using post-training quantization. Then we obtain this TVM operator graph, which we pre-process in order to group together which operations can be executed on the Gemini accelerator and which not. This is one of the main advantages here because the operators that are not supported by Gemini are directly defaulted to the RISC-V CPU. Just a note here, if you are interested in knowing how the requantization operator is merged with the Gemini operator, there are details on the paper about it. It's very, for me, it's very interesting. Finally, TVM builds the specific operators and selects the best schedule for each operator. If you already run the auto TVM process, this auto tuning process, it chooses the best schedule. It chooses the best schedule found by auto TVM, and if not, it defaults to a specific user-defined schedule. And then in the end, we obtain a C language project where each operator is a different C function, and we have a main entry point to run the complete network in a bare metal project. Very important here is to note that this C function, as said previously, we can generate here two kinds of C functions. Keep that in mind because it's important for the next slides. One that uses the default functions provided by the Gemini developers, and one that uses the intrinsic instructions. So this is more or less an example of how the TVM generated code looks like for a 64 by 64 matrix multiplication on a 16 by 16 Gemini accelerator. Here we have the configuration instructions. Then we have the move of the data into the accelerator's internal memory. Then we have the actual matrix multiplications. And in the end, we have the move out of the data. This is very interesting because this can get very complex if we start to touch a little bit the parameters I was telling you before. For example, this is how it looks like now with a different set of parameters. Here, instead, this is the same workload and the same on the same Gemini, 16 times 16. But now, instead of moving all the data into the accelerator's internal memory first and then computing using this available data, now the move instructions are generated inside inner loops, so that actually now the execution of the move instructions and compute instructions is kind of interleaved. So this is interesting because it's this schedule parameter space allows us to generate this kind of code where we can explore more interesting ways of executing a specific operator. Also, notice how the move out instruction that is at the bottom is executed multiple times inside a loop. This means that it's actually the accelerator is accumulating multiple results on its internal memory, and then we are getting them out all together, not one by one like the previous example. Notice how the accelerator, how the pointer address generation is now much more complex than the previous example. But because this is generated code, it's completely transparent to the user. This is very nice because if not, you would have to write this by hand. And as I was saying, this is a very heavy burden, perhaps not for this specific operator, but it can be for more complex operators. So let's get now to the experiments. This is our test setup. We use the Xilinx FPGA connected to a Linux host, which is running TVM. The parameters and the FPGA were selected so that we can do a fair comparison against the previous work that I will show you in the next slide. During the auto-tuning process, the host generates new instruction schedule proposals, compiles a C program, loads the program into the FPGA's DRAM, starts the CPU, and measures the execution time of this specific instruction schedule. The host then evaluates this execution time and generates a new instruction sequence depending on the result of the previous measurements. So let's take a look at our results now. This is the definition of the workload we tried to auto-tune. It's a matrix multiplication where all axes have the same size. As a metric to evaluate how fast the schedule is, we use the giga operations per second of our design. So let's focus on the left plot first. Here we compare the throughput of the best schedules found by our auto-tuning against the reference work that I was talking to you about. This was a work that also integrated Gemini into the TVM framework, but sadly it was not open sourced, so we had to use these numbers as were given in the paper. We couldn't actually run the code from that paper. We are comparing here the blue bars against each other and the red ones against each other. As we can see, our schedules are faster than the ones of the previous work for all workloads. Now let's take a look at the other plot, of the right plot. Here we compared the best schedules found by our auto-tuning, which uses the intrinsic instructions, against the reference C functions that were provided by the Gemini developers, which use the CISC type instructions. Here we are comparing the blue bars against the green bars and the red against the yellow bars. As we can see, our schedules are faster for almost all workloads. There is a very specific case for the 256 workload and the 512 workload, which are not better, where our schedules are not better than the CISC type instructions. There is a discussion in the paper in order to try to explain one of the reasons why this could happen. And finally, in order to test our integration on real-world workloads, we selected workloads from the Baidu DeepBench dataset. These are real-world fully connected layers, which are basically matrix multiplications. And here we also compared the best schedules found by our integration using the intrinsic instructions against the default functions provided by the Gemini developers. And here we can see that in this case, yes, our schedules are faster for all workloads. So again, here we are comparing the blue bar against the green bar and the red bar against the yellow bar. So what would be the next steps for this, work? So we would like to add support for other kinds of layers, convolutions, adding layers, depth-wise convolutions, and so on. We already have this working for the CISC type functions to generate C functions that use these CISC type instructions. But we also would like to auto-tune these operators, and this is still a work in progress. We would also like to demonstrate the power of this integration by accelerating entire deep neural networks. We already have also some object detectors working using the CISC type instructions and the complete workflow using TVM. But the goal, again, is to tune the entire network and get better results. We also would like to make a little more research in the improvement of the convergence of the auto-tuning search algorithm, because there are still problems with the feature representation of the auto-tuning model, and we would like to explore if we can use timing model simulators in order to not always generate code, send it to the FPGA, measure the code, and then get it back in order to speed up the auto-tuning process. And personally, I would like to open source the integration, which is in progress. I am preparing it. Hopefully, this will be submitted once I migrated the code to the new UMA feature from TVM. This is the Universal Modular Accelerator interface, which I think this integration could be a very good use case example for that feature. So thank you for your attention, and I am open to questions now.
Thank you very much for this presentation. So are there questions from the audience? I would have a question on, well, very nice presentation first. Thank you very much. I would have a question on your results where you compare against the CISC instructions that have been provided by the Gemini engineers. So the thing I'm particularly interested in is whether your scheduling search space, or whether you know, I don't know if these CISC instructions are actually open source, so you can check, but is your scheduling search space including the solution that has been provided in the CISC instruction? So is this a matter of your scheduling not being able to find the solution, or is it maybe not even possible? Well, that particular solution maybe not even possible because it's not in the search space. Is the question
That's
clear,
actually a very
or
good question. It's a perfect, valid question, and I have taken a look at this because I was also troubled about this behavior. And because the Gemini accelerator is open source, you can go in it, you can check how the state machines in the hardware generate the instruction sequence. You can see all of it. But although our schedule search parameter space is able to generate the same, or more or less the same schedule that the CISC instructions use, there is a feature which is only used inside the CISC instructions in Gemini, where there is some kind of load balancing done between which kind, how many of each kind of instructions is generated. That is only, this feature is only used when you use the CISC type instructions, and this allows Gemini to actually kind of simultaneously execute different instructions that have no dependencies between them. It's a little bit more complex to explain, but the main idea is there is a reorder buffer which takes these instructions, and it can tell the state machine that generates the instructions, hey, I already have a lot of compute instructions, generate a couple of move in instructions, and then it can do this kind of load balancing. I think it's there. I think it's there, the main difference, and we can't, generating the code with the TVM framework, replicate this behavior so easily, actually.
Yeah, thanks for the nice talk. Next question related to that. Can you say what's the overhead of whatever of these more small instructions that you have in the RISC-V? Is it like from the overall execution time? Is this significant, this execution time, or is it negligible compared to using the CISC function that just starts a state machine in the Gemini systolic array?
You mean like overhead in the specific instruction? Actually,
Yes.
there is no main difference in the overhead of each kind of instruction, because both kind of instructions use also this. Let's go here. So both kind of instructions use this ROC interface, and all of them are consumed by the controller of Gemini exactly the same time. So there is no difference there. These instructions are actually generated using C macros and are inserted into the GCC compiler directly as very specific assembler codes. So actually, in terms of the code size, for example, there is difference, of course, because you are generating a lot of more instructions, but it's still negligible. Also, I was not able to find a very important case where the CISC type instructions use a lot less of code than the intrinsic instructions.
Yeah, wow, sounds cool. Yeah, that you are at the same level as the library functions. Cool.
Any further questions? If this is not the case, then let's thank Federico again. Thank you very much. This was a nice talk. And
thank you very
much.
Move
on from here. The next presentation will be by Jen Liu. Jen Liu is here on the call, I think. Hi, Jen Liu.
Hello.
So Jen Liu will present the paper Deploying Machine Learning Models to Ahead of Time Runtime on Edge using Micro TVM. Jen Liu received his bachelor's degree in electrical engineering from Xidian University in China in 2012 and the master degree in microelectronics from the Technical University of Dresden in Germany in 2016. He's currently a scientific staff and working towards his PhD degree with the chair of highly parallel VLSI systems and neuromorphic circuits at the Technical University of Dresden in Germany. His research interests include radar signal processing, deep learning, neuromorphic computing, and autonomous driving. I think this is a perfect fit again to this workshop. So thank you very much for joining us today. And without further ado, I would like to hand over to you.
Okay, thank you for the kind introduction. So today I will bring a talk about the deploying machine learning models to the ahead of time runtime on edge using micro TVM. So first, I will give you the motivation, so why I choose micro TVM as our framework, and also why we need to build a code generator based on the micro TVM. And besides the pipeline of our C code generator, I will also discuss a little bit the strategy of how to register a new operator and how to register the accelerator in the pipeline. And to test our code generator, we also build experiments for the evaluation. And at the end, I will conclude and give you the future work directions. So motivations. We know that in the last decade, the machine learning, especially the deep learning, draw a lot of attention and really show some good results in a lot of applications, such as in the computer vision or natural language processing. And there are a lot of frameworks to help people train their models to achieve good results. For example, the TensorFlow, PyTorch, Keras, or MXNet. But we know that the training environment is different from the production environment. So production environment is a real place that usually we run our model. And in such environment, usually we suffer from additional limitations like the limited power budget or limited computation abilities. And there are another branch of frameworks help people to compile, optimize, and deploy their models into the production environment. The important candidates could be TensorFlow Lite, PyTorch Glue, OpenVINO, or TVM. But these frameworks, they invoke a lot of system calls. And we see that an operating system is usually required by building and deployment models into the if we use such kind of frameworks. And this may impact the target device number. So let's look at this figure. So this figure shows the increasing rate of the total number of connected devices. So we see from the 2020 to the future 2025, we can expect an average increasing rate of 13% of all the connected devices, which is the number of the devices that we could use. And if we categorize all the devices into IoT or non-IoT devices, we see the interesting is that the most gain is actually from the IoT devices. And we see the parts of the non-IoT devices is almost constant. So we can expect that the non-IoT devices, including the mobile phones, tablets, PC, laptops, and fixed line phones, go into a saturation phase. And then we should pay more attention to those IoT devices. So how to bring AIs or intelligence into that devices, because IoT devices usually suffer from the computation abilities. And for that, we see there are already some right tools to do this role. So TensorFlow Lite, Micro, or Micro TVM, they really target to deploy some pre-trained model to those bare metal devices. And both are the submodule of the TensorFlow Lite or TVM frameworks. And they all have the light kernel with the small memory footprint. But in my view, I see some limitations of the TensorFlow Lite Micro. For example, it depends on the C++11 libraries, and it's hard to expand operators in the framework. And also for any architecture of the backend hardware, it's not taken into account. And to solve or partly solve those limitations, micro TVM provides better solutions. So they are, it is free of the C++ dependency. And also they provide some strategies to tell users how to register your own operators, and also leave some room for the external accelerator interface. But so that's why I chose micro TVM compared to the TensorFlow Lite micro. But is that ideal for my deployment? I would say almost, but not yet. Because what I expect is an end-to-end solution for the deployment, which means that if I have a pre-trained model in hand and just want to get the executable binaries as soon as possible, so I still need to implement by hand the main function, for example, and also the compiling script. So that's why I need to build such a SQL generator to really give me the agile deployment ability. So based on the micro TVM, I built my SQL generator. It's a kind of a wrapper program on the micro TVM to bridge the gate between the pre-trained model and the backend chip. But besides, because the micro TVM, I used a lot of functionalities provided by it, like the front-end parser, the relay builder, or the C-source exporter. So I call it, it's a micro TVM based SQL generator. But specifically, I also address the following key features in my SQL generator. The first thing is that I try to give an end-to-end deployment solution. So if I have a pre-trained model and a backend chip, one-click solution is important for me, especially if the application due is urgent or any other time limitation is there. Another thing that I think somebody is ignoring usually is that for the development on the embedded system, usually debugging is harder than that if we have IDE, right? So rapid debugging is also a very important factor. And in this SQL generator, if I could also import some test data and directly generated the data on the chip for the quick debugging as a reference data, then it will be very nice. The flexible control is also another nice feature provided by the SQL generator, because currently, if I use micro TVM, I will generate some source code, but it's not well organized in a folder. So it's not, you usually need to really link the different libraries in different places. But my code generator use shell script to do this job, so that you will get serve content generated architecture for your backend chip. And the last thing is the expandability. So if usually, if we try to improve the computation efficiency on the edge, then accelerator is needed. And if we can find a way to really offload some specific computation intensive operators into these accelerators, that would be very nice. And unfortunately, we already have some interface to do this job. So now let's look at the block diagram of the code generator. So on the left side, you will see these are the required files for the code generator. This UMA stuff I will present later with another additional slide. So let's just ignore temporarily for that. So for a normal backend, let's see it's a normal CPU core as a backend. What you need for this code generator is only two things. One is a pre-trained model. It could be a TensorFlow or TensorFlow Lite or Onyx format. Of course, micro TVM support more front ends, but currently I see these three formats are the most popular. So I currently just support these three. Together with input data, it could be just some test data from your test data set and store those data in a NumPy array. So first, the first module in the code generator is the prepare IO. So this is just like a data translator to translate your NumPy array data into a header file, which is called the io.h. Basically, the data will be stored in a static array in this header file and included in your runtime. So after you have the inference results, and then you can easily compare it with the reference data to quickly give you the impression whether there's something incorrect happened during the deployment. The key component of the code generator is called micro AOT in the middle. It will take the pre-trained model as the input data, and the first stage would be the front end from the TVM framework. It's a parser to just translate this model to the relay graph. And if we skip those two UMA steps, and then the relay build will, lower this relay graph to the Tensor IR, and then export to the model libraries. But as I said, it's not well organized in the output. So I create another module called templates. So it's like a place that we can put some blueprint files there. Why we need this? Because usually for a backend chip, at least in my case, is that I already implement some classical or conventional processing applications on this chip, and I already have a mature compiling script or toolchain for that. And additionally, if I want to bring some intelligent stuff into this application, and then I need to really make the compiling precise, compatible with the previous one. So what you needed only just to put your makefile or main function into this template folder as a blueprint, and there would be some placeholder in that. And during the generation, it will generate the desired makefile for you, and also the top level main function for you. And there is a make.sh. So this shell script will move the generated libraries from the distributed place to a single place as called TVM module folder. It is well organized as a include folder and source folder. So we put the header file in the include folder and the source file in the source folder together with the make file. And this make file would be the one that's compatible with your previous compiling environment. So basically, this is the whole thing for this SQL generator. And with it, you can ideally get the executable binary after this one click. But I would say that usually you will meet some accidents during the deployment. One of the most common problems you may meet is that there's some customized operators contained in your model, which is not recognized by the front-end parser. So in this case, what could you do? So there are two methods. The first one, which is the straightforward and naive one, is by calling the existing relay operators, which means that we can use a combination of relay operators to interpret any customized operator contained in your model. What you should do is only to modify some Python files in the TVM framework, and you don't need to recompile your TVM framework. So you just go to the front end file and find the convert map. So it's basically just a dictionary variable, and you put this new entry as your customized operator, and then realize a conversion function as the value of this directory. So this conversion function should be a combination of the different relay operators, which is already available in the framework. So after that, if you rerun the generation, it should recognize this customized operator and then deploy it to the CSOS files. But another case would be it's not possible that you use any available relay operators to interpret or to reproduce your customer operator contained in the model. In this case, you need to really create a new operator, a relay operator, and then you need to modify multiple C++ files and all together with Python files to really register that. Some instructions already available in the web page of the TVM, but I will repeat it a little bit here. So first step would be to define an attribute node, for example, the data tab, and register it, register this attribute node, and then write the type relation. So these three steps is in the C++ domain. And then your key point is that you need to define the strategy for that. And this is in Python domain, you need to define the computation and the schedule for that. After that, you come back to the C++ domain and create a relay call node for that, and register this operator to the relay. And of course, this relay exists in the C++, and then you need to back to the Python file to really create API for this new operator. So in this way, you create a new relay operator, and then you need to recompile the TVM framework and then rerun the generation. Another case is that we know if we want to register a new computation node at the end. For example, if we have an accelerator mounted together with a core in the edge device, so what could we do? Currently, TVM already provide a mechanism called BYOC, so bring your own accelerator. But after some personal experience, I didn't really much like it because it's a cumbersome kind of. And fortunately, in the last several months, I see that thanks to the community that people try to alleviate these things and provide another interface called UMA, so a universal modular accelerator interface to alleviate this problem. So how could I insert this UMA interface into my pipeline in this code generator? So if we look at here, you will see that as if we are a backend chip vendor, so what should we provide for UMA? So ideally only two files, one backend C++ files, which contains the C APIs for your accelerator, and another file is a Python file. It's called backend.python to tell the TVM Python framework that how to be compatible with the customized accelerator C APIs. So we insert this UMA interface between the front end and the relay build step. So after the front end convert the model to the relay graph, and then you need to really register some specific pattern operator. So this pattern operator is those operators that could be accelerated by your accelerator. And a partitioner will partition or divide this relay graph into two subgraph. So one is pattern relay. So this graph contains those operators could be accelerated, and the non-pattern relay. The non-pattern relay will go through the conventional TVM default pipeline. And the pattern relay will go through the customized multiple passes defined in your backend.python, which will lower your relay operator to the Tensor IR. And finally, those themes will send back to the mainstream, and then we use relay build to translate this TIR to the C source files. So in this way, we could also insert, so leave some room to insert the UMA interface into this code generator. But unfortunately, because this UMA interface is so fresh, so for this evaluation, we don't have enough time to really integrate that into our tool. So we plan for the future work of this part. And how to evaluate our code generator. So we built an evaluation setup and experiment of the hand gesture recognition to check our code generator. So the setup is using the Spinnaker 2 chip as the backend. So Spinnaker 2, as my colleague Bernhard introduced in the first presentation. So it's a digital brain-inspired neuromorphic hardware with multiple processors. So in total, it contains 152 Cortex M4 processors. So each processor is one processing element called PE. And together in each processor, together with a floating point unit. And in each PE, we have 128 kilobyte SRAM and the machine learning accelerator, which is actually a 16x4 macro-array in each PE. So that's so we can see that because in this backend chip we have the machine learning accelerator. So in the future we are potential to insert to bring through the UMA to bring the accelerator into the pipeline. And actually for this task, this hand gesture recognition, we use MU sensor mounted in a glove to capture the gesture of the hand. And the data will send to a laptop via the Bluetooth wirelessly, and then forwarded to the backend evaluation board. But this model is very small, so it only contains 1,500 parameters. So it's totally fine that we can accommodate the whole model in a single PE. But still, we use 2 PEs for that. So one PE is the pre-processing PE, and another one is a classification PE. So all the classification, namely this model, is deployed into PE1, and the pre-processing PE is charged of some data collection, buffering, and data movement to the specific memory place. So the model, so how does the model look like? They have 2 stages. So in the pre-processing stage, we used 6 channels with 1D features, and together with decimation of factor 2 as a feature extractor. And then we use a GRU layer and a fully connected layer for the classification, followed by non-linearity of softmax. So finally, we will have 21 classes as the output. So there would be 21 gestures defined in the task. And we achieved the 96.6% for the gesture recognition. So after that, we really check and see that the deployment of the model on the PE1 only requires minor post-code change. And the code in the PE0 is manually implemented. So with a conclusion, so we built a micro TVM based code generator for this agile DNN deployment on edge devices. So if you just prepare a pre-trained model and the backend chip with a correct compiling script, you can with one click to get your executable binaries. And this end-to-end code generation only require minor efforts for the applications. I mean, to insert this model into any pre-processing classical applications. And this code generator is also friendly to be inserted into a tool chain off the shelf, which means that if you already have a tool processing chain for your classical applications, and then the generated files and compiled to a library could be a library in parallel with any previous libraries that you have in your applications. So in the future work, we see that UMA is a promising interface to offload any specific computation-intensive operators into the accelerator, and we definitely will pay more attention to this interface and try to offload the patent operator. For example, for us, it would be comp2D and matrix multiplication to the accelerator using UMA. And another thing is that we will benchmark our code generator with other state-of-the-art in terms of code size, inference latency, or the memory footprint. And basically, that's the work I have done here for my presentation. And thanks for your listening.
Jen, thank you very much for this presentation. Very nice. And again, this is the round for questions. Are there questions in the audience? If there's no questions, I would still have one, I'm sorry. Jen, you're also using the Spinnaker 2 hardware. I was wondering, from the perspective that you presented, if I understood correctly, you have this micro TVM framework to generate ahead of time code that you could compile ahead of time. Will this then run similar to Bernhard's approach with one layer per PE? And would you then also compile only layer by layer, or can you compile with your framework an entire network end to end?
It's different. So in my case, I compare the entire model. So it contains multiple layers. For example, here, this is if you take the filter as one layer, so it would be a filter, so a double of the filter and downsampling layer and the GRU layer, fully connected layer. So it will be a heterogeneous layer type contained in this model. And this is all compiled by the code generator. And I deploy that whole things into a single PE.
Into a single PE. So in your case, you would run, you have the Spinnaker multi-core, but you would run one neural network within one PE.
Exactly. So in this test case, this is just the first trial for this code generator. So we only use one single PE as the backend. But you know that Spinnaker 2 has multiple computation nodes. So we're also quite interested in how to really use the TVM to really split the graph to subgraphs. And for each subgraph, we can deploy that things to a single PE. So we can really efficiently do the inference with a large model on the Spinnaker 2.
Fantastic. Thank you very much. Thank you for clarifying.
I just wanted to add something because I am also working on a similar problem for the multi-core system. So let's get in touch and discuss ideas on that.
Yep, that's welcome. And also I'll want to talk with other people for this issue.
That's very good.
Yeah.
Fantastic. Are there any further questions? Okay, that seems not to be the case. Then Jen, thank you very much again for this very nice presentation.
Thank you.
So this concludes the, this was the last talk of our workshop. So this last presentation basically concludes the workshop on compilers, deployment and tooling for Edge AI, CODAI, at Embedded Systems Week 2022. We had 9 high-quality contributions, out of which there were 2 keynotes, one from the industrial perspective, one from the academic perspective. In total, 5 papers, which, by the way, the accept rate was not 100% in case you were wondering. So we had the chance to really select high-quality papers that were presented today, and we had also 2 invited talks. So with this, I can only thank you, everyone, for contributing your research results, participating in the discussions, and making this workshop a success. From my point of view, we have met the purpose of the workshop, namely to bring together academia and industry and to trigger interesting exchanges and discussions. I think we are looking forward into a very exciting future. This was a successful workshop. We hope to repeat this next year again. And since at the current times, many things are virtual, please feel free to reach out with one another. There's GatherTown where you can meet still. The papers will be published afterwards in the proceedings. So I think, Federico, you just mentioned it. It would be very nice if this could be a nice community to be built. So get in touch with one another, do exchange more ideas, and then hopefully see you next year again.
Yeah, I hope you too. So thank you for all.
Thank you
Thank you very much.
Bye.
Yeah, thank you for the organization. Very nice workshop.
Thank you.
Bye then.
Bye-bye.
Goodbye.
Good evening. Bye bye.